Good morning, distinguished guests, speakers, and all the participants. On behalf of the organizing committee, I'm honored to welcome you all to the 7th International Conference on Geoscience and Earth Resource Engineering 2025, Day 2. This event is an annual conference held by the Faculty of Mining and Petroleum Engineering. With me, Sekar Indah, as the Master of Ceremony today, hosted here in Bandung Institute of Technology. This international conference brings together professional, academics, and practitioners to discuss and share insight on the latest advancement, technology, and groundbreaking research in the field of geoscience and earth resource engineering. We firmly commit to give significant contribution to the development of research and facilitate the collaboration across disciplines. In this great day, I would like to extend our sincere appreciation again to our honorable guests, the organizing committee, our sponsor and partner, Yayasan LAPI ITB, Direktorat Riset dan Inovasi ITB, Purnomo Yusgiantoro Center, and Migas Hulu Jabar ONWJ, and also the supporting by Paragon Innovation and Technology, who support the implementation of this event. And of course, all of our great speaker and the attender of today's agenda. As your safety is our utmost priority, before we start the event, let us put our full attention to the safety induction video, which will be played right now.
Safety Induction, keamanan, kesehatan, keselamatan kerja dan lingkungan di ITB. ITB berkomitmen untuk mencapai kinerja terbaik di bidang keamanan, kesehatan, keselamatan kerja dan lingkungan yang mencakup aset sumber daya manusia, bangunan, perawatan, dan kekayaan intelektual. Oleh karena itu, ITB mengharapkan kesadaran setiap individu yang berada di area ITB untuk turut berperan dalam mewujudkan kondisi keamanan, kesehatan, keselamatan kerja dan lingkungan yang kondusif dengan memenuhi pedoman keamanan dan K3 yang berlaku di lingkungan kampus ITB sebagai berikut. Setiap individu diminta untuk meluangkan waktu memahami lokasi kegiatan dengan melihat peta lokasi yang memuat jalur evakuasi, lokasi pintu darurat, tempat berkumpul darurat, tanda kedaruratan, lokasi pemadam api ringan, dan kotak P3K. Terdapat pintu darurat dan assembly point atau tempat berkumpul yang aman di setiap gedung. Jika diperlukan evakuasi, panitia pendamping atau satpam akan memandu. Setiap individu wajib turut menjaga kebersihan gedung dan area dalam ITB, serta membuang sampah pada tempat sampah yang telah disediakan. Setiap individu diimbau untuk tidak meninggalkan barang tanpa pengawasan karena alasan keamanan. Tidak diperkenankan merokok di dalam gedung dan di kawasan kampus ITB, kecuali di area merokok. Pastikan puntung rokok mati sebelum membuang ke tempat sampah. Harap dipahami bahwa keberlangsungan kegiatan dan acara adalah di luar dari pelatihan keadaan darurat. Jika alarm tanda bahaya terdengar, maka nyata terjadi kondisi darurat. Jika terjadi kondisi darurat atau menemui benda atau orang mencurigakan, kecelakaan, atau kondisi tidak aman lainnya, silakan menghubungi petugas keamanan terdekat atau nomor darurat ITB di 022 250 02 04 untuk area ITB Gadesa dan 022 860 10 020 untuk area ITB Jatinangor. Demikian pedoman ini kami sampaikan. Terima kasih atas kerjasama dan perhatian Anda. Utamakan keamanan, kesehatan, keselamatan kerja dan lingkungan.
Okay, thank you for the safety video. We hope all of you will understand the essential safety procedure to support the safety of this event. And for today's agenda, we have 3 plenary sessions, technical session, oral presentation, and poster presentations. For the first plenary sessions will be dedicated to geothermal engineering, followed by the oral presentation from geothermal engineering. The second one is the plenary session from petroleum engineering, followed by the oral presentation from the petroleum engineering. And the third one is the plenary session from the geophysical engineering, followed by the oral presentation by the geophysical engineering. We also have the poster session at the between the second and the third plenary session. And without any further ado, let us start the first plenary session discussing about the geothermal engineering aspect that will be delivered by Bapak Heru Berian Pratama and moderated by Bapak Calvin Lumbangaul. To Bapak Calvin, we invite you to come to the stage.
Yes. Good. Okay. Good morning, everyone. I would like to welcome all again to the second day of our 7th ICG conference, and I hope all of you are ready. And of course, now we would like to start with the plenary session with a topic of geothermal engineering. And I will be the moderator for this session, and we have our speaker, Dr. Heru Berian. And who's next? Okay, before we start, I would like to introduce our speaker. So, Mr. Heru Berian Pratama, STMT PhD. He's currently an assistant professor and senior researcher at Institute Teknologi Bandung, of course in the geothermal engineering department. And Dr. Berian received his education, master degree in geothermal engineering at Institute Teknologi Bandung in 2015, and he received his PhD in engineering from Kyoto University in 2025. And Dr. Berian already start working as an assistant professor from 2017 till now. And then of course since 2022, Dr. Berian is already a lecturer and senior researcher in Institute Teknologi Bandung. And of course also, maybe all of you already know, start from yesterday, Dr. Berian is officially a head of department in geothermal engineering department. Yeah, and I think we can start the session for today. I would like to invite Dr. Berian to the stage. Please welcome and please give applause to our speaker. So, I think we can start. Dr. Berian, the stage is yours.
Okay, thank you very much, everyone, and also for coming here in this morning session of the geothermal engineering. I would like to introduce myself again. My name is Heru Berian Pratama, and currently I'm head of geothermal master program in ITB. And as you can see, this is my profiles. I mostly focus on the research and also the project from the geothermal, and focusing on the geothermal reservoir modeling and also simulations and for sustainability. Okay, in this occasion, I would like to share our latest research regarding the advanced reservoir modeling and optimization for sustainable geothermal power generation, integrating the simulation-based resource assessment, thermodynamic cycles, selection, and also system optimization, because we would like to combine all of our information and research into one single framework for sustainability. Okay, for the reference, this is our resource of our presentation here. It's already published in 3 high reputable and impact factor journal in geothermal, and 1 for in renewable energy, all of them from Elsevier's, and all of them is for me as a first author and a corresponding author also. Okay, the outline of my presentation is divided into introduction, research aim and scopes, and the state-of-the-art of engineering approach, which is we would like to talk about numerical modeling, resource assessment, integrated framework, and thermodynamic, and also the contribution and future work of the study. If you like it, or we will continue to do the research. Okay, the research background is, as far as we know, the geothermal energy, a critical renewable resources, offer continuous power generation, but it requires comprehensive assessment frameworks for sustainable and effective utilization. Thus, the current challenge here is that the lack of robust conceptual models that accurately depict the fluid flow within the reservoir and insufficient methodology to quantify uncertainty in the reservoir itself, also the performance and behaviors, and the absence of schematic approach in selecting the most suitable power generation system in certain type of the geothermals. And also, there is an improper how to integrate all the models into one single framework for the long-term exploitation. And also the purpose of this research is that to address the gap by integrating numerical reservoir simulation with thermodynamic principle for the sustainability with, and it also enhance the accuracy of the results, and also evaluate the key factor, and also capture the case, for example, scaling in the productions, and also identifies the optimal generation power system based on our research, based on the concept conventional power generation and also the latest technology of power plant. And the applicability of our studies and also the methodology is applied into the Bedugul geothermal field in Bali Islands. This is the red box indicate the area of our study, and it has, as you can see, there is a lot of volcano inside the caldera, and it makes a complex how we define the geothermal system. That's why we need the reservoir modeling to characterize the geothermal system before we are using another approach of our methodology. And this is the scenery of the Bedugul geothermal field, which is a very good sightseeing. There is, as you can see on the top left corner, there is 3 lakes, and also there is several volcano inside the caldera, a huge caldera, and as you can see there is a beautiful scenery, and also it has 3 deep exploration wells from 2.5 until 3 kilometer depth, which is a very good data for us to build a model to know this, to characterize the system of the Bedugul geothermal field. And this is the outline of the preliminary Bedugul geothermal system. As I mentioned it before, this is the geomorphology and also the geological map indicating the geothermal the geothermal lithology in the Bedugul geothermal field, and also it has 3 deep exploration wells, and from the 0 meter above sea level until the bottom of the well indicate it have high temperature, which is very good for us to build electricity within this system. And also from the geochemist data and also from the MT data, it showed that from the geochemist, it could see that the sample from the geothermal wells, in this case BL number 3, indicate is the source is from the reservoir, and also from the MT data in the top left corner, indicate it has a steam cap rock that surrounded the caldera with a doming shape below the Mount Tapak, which is the center of the caldera. And from the previous conceptual model on the right corner indicate that it not appropriate for us to identify the system because it could not describe clearly about the reservoir, heat source, the heat and the mass flow within the reservoir, and also isothermal temperature. And it could be misleading information if we do the the production scenario that decided the well targeting area. And this is the workflow of our first approach using the numerical model. We start from the review from the geoscience data, and then we translate it into the conceptual model, and then change to the numerical model, and then run the and then put the and the last one is we are using the relative permeability and also capillary pressure. And this is the data on the left yellow box here. And also after that we run the model and validate with the observation data. In this case we are using PT data to make sure that our model is in high accuracy. And this on the bottom part, it's showing the figures. For example, this is on the right figure is 3D block models of the Bedugul geothermal field, and also the blue box that we are rotating based on the major fault. And on the left side, it shows the boundary condition. The top, the yellow one, and in the center is the side boundary, and the bottom one for the bottom boundary condition. And on the left table shows that the material property that we assign into the Bedugul geothermal field. And this is our model validations. We are using TAF2 simulator to do the modeling. And as you can see on this figure, the graph shows that it has a good accuracy because we are using this statistical evaluation using root mean square error indicates the exploration wells indicated by code of BEL or Bedugul. It average have 2.9 degrees Celsius root mean square error, and for the temperature core holes, the average is 6.3 degrees Celsius, and we are using the scatter plot to define is this on the 45-degree line, and it shows already that the model is in high accuracy. So we are believe that our model is ready to combine with the other framework. And this is our result based on the permeability setting with when we build the numerical modeling of Bedugul. The first one, we put the tight permeability in the caprock area here on the top left corner, and then surrounded by the relatively low permeability, and it resulted accurately the geothermal system within the reservoir. For example, in this case, we could generate the system that have, for example, in this case, that in the hot hydrostatic liquid, and then followed by the vapor dominated zone, transition zone, and the liquid zone. So we believe that this is one of the complex our model in around the world regarding the geothermal system that has a steam cap above deep liquid reservoir with the transition zone in between. And also from on the right corner, right figure, it shows the heat and mass flow within the reservoir. One of the unique is that from the steam cap, it shows that it has a counterflow mechanism because the steam goes outward and then hit the caprock, and it could be resulted in heat loss that change the steam into the condensate, and the condensate, because it has high density, it will become forward. It become continue, something like that. It's like the buoyancy, and then resulted in the counterflow mechanism. And the bottom one, it shows that the magnitude of the heat source that affected the reservoir. And following that, we identify the isothermal and the gas saturation distribution within the reservoir. On the left, on the bottom one, it has 5 heat source indicated between the volcano. For example, the Mount Tapak is the highest one based our results. And also in the bottom one on the left corner, it shows the outflow of the heat and mass goes from the heat source into the reservoir and also to the heat sinks. And following that on the right corner, it shows that the gas saturations with the maximum is 0.7. It shows also the different elevation from the gas saturation in the top figure, and also from the bottom one, it shows that the distribution of the temperature. And it could be good information for us to delineate the high temperature area, which is higher than 240 degrees Celsius, to develop electricity from this area and to produce the heat and mass flow actually. And also the comparison from the Bedugul and also the one of the famous vapor dominated around the world, that the Bedugul characterized by the high temperature and pressure compared to the other geothermal system that has vapor dominated, and we identify based our calculation classification from the baseline is that the major geothermal field, as you can see, is on the Lardarello, the geyser, and also Darajat that has 34 bar and 200 degrees Celsius as a major geothermal field of vapor dominated. However, Bedugul, included in Wayang Windu and also Matsukawa in Japan, has a higher temperature, and it shows that it's close to the phase 1 that premature. And following that, the post-mature is the Patuha geothermal system, and this is one of the key finding and novelty of the studies. And also this is the updated conceptual model based on the numerical simulations. It shows that also it indicate the heat source, reservoir, cap rock, heat and mass, and also isothermal, and also the lithology based our numerical model. And it gives information for us to see the detail in the bottom of the reservoir, below the subsurface. Okay, following that, we combine the numerical model as a core of the study to the other methods. For example, resource assessment, wellbore modeling, and also silica scale disposition modeling, and the last one is thermodynamical modeling of the power plant into one single framework to do the sustainability. But before that, we decide to plan of the development of the field based on selecting the power plant size, and then the production rate, injection rate, and also the temperature for injection. And the following is the makeup well to supply a certain kilogram per second of mass flow to the power plant. And on the top corner indicate this is our modeling approach based on the domain of the modeling itself. For example, the geothermal reservoir. The geothermal reservoir is all of them, and from the well is the well bore, and also from the top is the power plant. And this is the workflow of resource assessment. We are using the latest robust method that we are published in the high reputable journals. The first one is we define the simulation objective, and following the next step is to identify the parameter and uncertainty, and selecting the design of experimental design and response surface methodology to build numerical model based on this case, and then run simulation based on the generating of this algorithm, and then analyze and check it is fit with the residual plot. Yes, we built the proxy equation to do the Monte Carlo simulation to generate the cumulative probabilistic function and also the probabilistic distribution function to make a probabilistic of the resources of the geothermal field. And this is the design of Plaquette Burman, one of the experimental design that we are selected. Because why? Because Plaquette Burman is one of the simple compared to the other without sacrificing the result. For example, in this case, the Plaquette Burman with 4 key parameters that we identified. For example, permeability, porosity, feed zone, and also reinjection. The following number is on the top corner, and the combination of its parameter based on the Plaquette Burman, it needs only 12. So it could reduce our time that with laborious time to do the calculation, to do the modeling using this Plaquette Burman. And following this running, we are following that, how we produce the heat and mass within the reservoir. We are using the wellbore modeling. There is several types of wellbore modeling, and based on our result, one of the produce highest accuracy with the observation data is that we are using the Hagedorn-Brown correlation with the empirical equations show on the top corner. And this is a schematic how we produce, for example, in the steam zone and the deep liquid reservoir. And the result based on the wellbore modeling is we running also with the Tufte model to generate the mass flow and also the enthalpy from the reservoir to the surface. And the results show on the table, and also the accuracy show on the left figure with the production test, and also the modeling, and also the wellbore modeling result on the center of the figures. Okay, this is our result when we produce the heat and mass with using the well-born modeling of Hagedorn Brown. And this is the resource assessment using a black hat bromine design based on our formula to calculate the power capacity using on the top corner. And the input is on the in the graph below that has enthalpy, mass flow, total mass flow, and also steam. And we calculate it using this simple equation on the top. And the result is shown in the table on the left one of 12 run models. It shows it can be like that. And generating, and based on the result, we check the residual plot. And based on the standard residual and also fitted value, standardized residual and observation order, it shows that it has a good accuracy from the model of the black hat bromine design. And following that, we are generating the proxy equation. As you can see, this is the equation that we are generated, and check again the accuracy, and shows that the data model from the observation model shows in the 45-degree line, which is so the good accuracy of the model. And following that, we are using the Monte Carlo simulation to generate the probabilistic assessment, and resulted P10, P50, and P90 is 78, 84, and 90 megawatt electric respectively. And to do following that, based on resource assessment, we also check it is when the silica appear when we do the production. That's why we have to calculate the minimum temperature to be reinjected into the reservoir. So in this case, we are using the silica modeling based on the data from BL2, and using on the left figure, we estimated what is the minimum temperature that silica appear. And based our calculation, the minimum temperature is 130 degrees Celsius, shown in the top left figure here, and it's controlled by the amorphous silica. And after we get the minimum temperature into the reservoir, we build the workflow of the thermodynamical modeling based on the bound variable of the single flash, which is the conventional geothermal power plant, and the latest one is the double flash, and also the flash binary. So following that, the single flash, we could generate additional electricity from the brine separator of the waste heat utilize the second separator or ORC cycles. As you can see, this is our workflow with the bound variable, with the optimum target is the power output and the efficiency of energy and also exergy. And this is a schematic of the double flash and flash binary power plant in the calculation, and it also published in the renewable energy. And this is a schematic, simple schematic of the power plant itself. The differences is we are using the second separator for double flash that utilize the waste heat from the high separator pressure, and also and from the comparison, the flash binary, we are using binary, or we are using the organic Rankine cycle that has a lower temperature boiling point. And this is our result of the calculation of the thermodynamic. We are divided into the left figure and top on the right figure. The left figure focus on the double flash, and we are calculating for the optimum value of the separator, because the pressure of the separator will define the optimum value from the generation of electricity. And based on calculation, the optimum value is the 7.9 and 2.8 for the high pressure and low pressure respectively of the double flash, while for the flash binary we are also check with the thermal efficiency, exergy, and also pinch point working fluid consumption rate, and also brine consumption rate. And following this, we identify that the turbine inlet pressure is 15. In this case, we are using the isopentan and pentan, which is the pentan is highest in exergy, while for the consumption rate, the lowest is pentan, which is very good. So in the next calculation, we are using pentan to do the modeling of the ORC. And to generate the electricity, in this case, we are using, we identify the 60 megawatt for the electricity of the power plant of the Bedugul. And following that, based on our calculation, it needs at least 10 for us, which is not which is not able to do the build a well pad on the purple area. So we put the well pad outside the conservation forest. However, the targeting of the wells is go to the outflow area in the below the Mount Tapak, as you can see on the center figure. And also from the upper part is the location of the model itself based on the actual data from the observations. And this is our results based on the thermodynamical model, the wellbore modeling within the reservoir, and it produce estimate around, for example, the enthalpy is around 1,300 kilojoule per kilogram, with the flow rate is around 45, on average is around 35 to 40 kilogram per second, and also the steam is around 15 kilogram per second. And this is the injections, because without production, without injection there is no production. So that's why when we produce the heat and mass from the wells, we should also inject it into the reservoir. And this is our calculation based on injection and also the production with a different scenario of the double flash and flash binary. And it shows that the double flash can prolong the makeup well. Why? Because it's very important for us when we are deciding for the sustainability. And as you can see, the result is relatively different. However, if we look into the area below the graph, indicate that the double flash can extract 1 megawatt more compared to the double flash binary, and it can prolong 2.5 years of the makeup wells. And how we compare the double flash and also flash binary within the change of the reservoir. For example, in this case, we are using the gas saturation, temperature, and also pressure from the initial on the top figure, following the 5 years, 15 years, 20, and also 30. Based on our results, we could not identify the change, the differences between this scenario. However, if we are looking into the detail from the behavior of the wells, for example, in this production well, it shows that a different value for the double flash on the left one, and on the right one it shows a different behavior on the northern part and southern part of the geothermal field when we do the production. The northern part, because there is injection, it has a stability of the production decline, because it can it supported by the reinjection to able to stabilize the pressure. However, in the southern part, steam cap is developed more and thickening and also widening, because when the mass and heat produced from the southern part, it resulted the highest decline pressure. The highest decline pressure is mean that it triggering the boiling and also make the boiling more massive. The benefit of this one is that it increased the enthalpy and also increased the productivity, because we want to produce the steam instead of the water from this area. And this is our result, shows that based on our finding of the numerical model, the temperature become lower due to the reinjection. And the green one shows that the temperature is the 70 degrees Celsius, as you can see on the small one on the big green on the top corner, and while on the blue and also the brown indicate the changing of the gas saturation from 0.4 to 0.6 of the gas saturation, and also 0.6 for the yellow one, which is it increasing the enthalpy and also increasing the steam flow, which is good for us to do the production. And also the change within the reservoir, as you can in the bottom of the conceptual model, in the 30 years of the exploitation. And our key finding is that the temperature decline in the northern area was caused by the return of the reinjection fluids. However, in the southern area can be characterized by the large increase of the gas saturation and thickening, and also the expansion of two-phase or vapor dominated zone due to the result of the decline of the pressure that triggering the boiling and also the massive of the boiling itself. The contribution of this study is that we offer a comprehensive framework addressing the key factor and also impacting the power generations. And also demonstrate through a case study the research provided valuable insights and also the methodology to improve the efficiency and longevity of the geothermal energy system, advancing and utilizing the geothermal power generation resource significantly. And one of the interesting feature from our study is that we still develop a new methodology. For example, in the future works, because we do the modeling conventionally, it takes a lot of time, it takes a lot of iteration, trial and error. However, since we in the area of the machine learning, it could be integrated with the machine learning to make the simulation faster without sacrificing the results. And also, because it also is a practical framework, we also could integrate with the financial and risk analysis to make sure which one is good in return regarding the financial analysis using some, because we are using so many data in here, probably the best one is using the complex, solving with the complex objective functions using the optimization methods. There are several optimization methods that we could apply in this study. And also, because we are using we assume that the reservoir is the pure water. However, in the real case, there is a lot of variable in the fluid. For example, there is a lot of volatile gas, and also that the reaction between the fluid and also the rocks that could change the property of the rock itself. So that's why in the future we could also simulating the reactive transport of this modeling. And also we are, because we are not included the geomechanic in the process, it could be in the future we could be examining the temperature variation of outer stress distribution influence rock mechanical property using thermo-hydromechanical simulations, which is very interesting for us in the future. And the last one is that because it showed that more than 300 degrees Celsius in the top of all wellbore, based on our study, this model, this geothermal field, Pedugul, has a potential of the supercritical temperature. So that's why we want to deeper study again, to do the research again, the study to check is there any potential of the supercritical, because the supercritical is 10 times higher in the production capacity instead of the conventional. So in the future, we could check is there any potential in the bottom, and if yes, it will be interesting when we build the model that could be shows the characterize the conventional system on the top, and the bottom one is the supercritical temperature. Okay, that's all my presentation. Thank you very much.
Thank you so much. Please give applause to. Okay, now we have a question and answer session. So I think we have 10 minutes. So like 2 or 3 questions. So we just heard that very comprehensive presentation, Dr. Heru Berian. Thank you so much. And now we have, we already heard the approach, the very comprehensive that you integrate the geoscience, reservoir production, and thermodynamic of the power plant into your study, and it gives a very promising result, especially as all of us know that in this energy transition period of time, we really need that we have alternative to the energy, especially for the clean energy. So I think now we can have a question session. Please, if you have any question. Yes, we have one here, and also one here. And also please remind me, we have also the online participants. If there is any question from the online, you can just let me know, yeah? Thank you. So I think, please start with your question.
Thank you. My name is Egi. So thank you for your sharing because it's so insightful, Pak Heru. One of the main interesting part to me regarding the silica precipitation, if I'm not wrong, in your presentation, you try to identify the minimum temperature when the silica will precipitate. Is there any following work regarding how big the impact of this precipitation to the decrease or like formation damage in oil and gas to the decrease of permeability sort of thing? Because in your case in Belugu field, if I'm not wrong, the range of reservoir permeability are 10 to 100 millidars, if I'm not wrong. So in that region, probably the slight precipitation may impact the decrease of permeability essentially. I think that's all. Thank you so much.
Okay, thank you very much for Mr. Egi for the question. Yes, it's really interesting why we have to calculate and estimate the minimum temperature to identify the precipitation of the silica, because the silica, if there's occur in the facility, for example the pipeline, so it will be lower the production capacity. However, if the silica occur in the production capacity will be much lower, and if that happens, it will be penalty from the developer. So that's why we have to establish the modeling of the silica to identify the minimum temperature when we design the surface facility. For example, in this case is from the thermodynamic principle, because when we do the production, we also inject it to come back to the reservoir in terms of the fluids, the rates, and also the temperature. The temperature is very critical because the lower temperature, it means that we could extract more energy. However, there is a threshold from the silica precipitation, and there is several silica in this case because it's nature from the geothermal system, and it also includes all the fluid in the geothermal. However, it's different from the case by case. In the Bedugul case, the minimum temperature based on calculation is 130 degrees Celsius, and it controlled by the amorphous silica, and it's a base of our calculation, the thermodynamic, when we do the reinjection. And for this one, we identify the minimum pressure separation in the separator based on the temperature saturation to be injected back to the reservoir. So that's why the basis of our calculation for the thermodynamic is on the silica scaling. Okay, thank you very much.
Thank you, Mr. Egi. And the second question maybe from here. Yeah.
Okay, thank you, Mr. Berian. Let me introduce myself. My name is Giri Tegararya Wibisana, and thank you for the time. And I very interesting with your presentation because I'm from Bali too. So in your presentation, you highlighted about uncertainty as an unresolved problem, and I want to asking you about how does the model that you developed in this presentation will quantify and manage about this uncertainty. Especially about regarding the estimation of resource and the reservoir life. And is it possible to analyze about the different risk scenarios about on your presentation? Maybe all of that's all of my one. I want to ask about your presentation.
Okay, let me recap the question. The first one, you talk about the uncertainty, and the second one, talk about the scenario of the productions.
Yes.
Okay, thank you very much for the presentation. It's very interesting because there is a lot of uncertainty when we do the modelings regarding the reservoir modeling, wellbore modeling, and then also silica scaling modeling, and also thermodynamic modeling, and combine all of them, it could be multiply the uncertainty. And focusing on the resource assessment, it means that we are focusing on the reservoir, the characteristic of the reservoir, the property of the reservoir, the dimension of the reservoir. It's a lot of uncertainty. If we have so many data, we could reduce that uncertainty. However, in this stage, in the exploration stage, we have limited data. But how we estimate accurately of the potential of the resources? So we are using the numerical model that combine with the latest robust method of the experimental design and response methodology. There are many type of this one. However, we choose this one because it could be it can give us a better accuracy in terms of the one, capture the uncertainty and how the effect of the uncertainty. So that's why instead of using deterministic approach, we are using the probabilistic one. So we identify based on our trial and error and also based on the previous result. The key finding is that we don't know exactly how the big is the permeability, how the big is the reservoir, what is the good fit zone when we do the production and targeting the wells, and also what is the number of porosity. That's why we change all of the parameter all the parameter within the reservoir. For example, this one we are using 21 material property with a different types that we inputted into the reservoir model to capture the uncertainty. The detail of the focus on uncertainty we have been published in the geothermics. You could read that one and download it from the uncertainty, because we develop the probabilistic one. So we want to make sure that our model is good accuracy, and we could give us the optimistic value when how big is the resources instead of using the deterministic. And the second one is the scenario of the production. The scenario production, because this field, it has steam cap above deep liquid reservoir. It could be interesting for us if we produce the main steam, because the steam is relatively easy for us to produce. There is no excess of the brine waste heat. However, the brine that we could produce in deep liquid reservoir, it could bring another or the excess heat when we separated the fluid of the gas and steam, and also with the brine in the separator, and the brine after the separator, we could generate additional electricity using the binary and also double flash. And also deep liquid reservoir, there are so many multiply of the production scenario. In the future, we could use the complex system with the optimization results, and we still do in our laboratory you are using the optimization when we do the different scenario. And the injection scenario is one of the important, because we believe that there is no production without the reinjection, because we take and give also back to the reservoir. Because if we take off the fluid from the reservoir to the surface, could be harmful from the environment. So that's why we inject it back to the reservoir, because it gives us a pressure support to the reservoir. So it means the decline rate is become much lower compared to if we take all of them and not injected back to the reservoir. That's all. Thank you very much.
Thank you, Mr. Berian.
Thank you so much, and also the audience. But unfortunately, I think because we have a time limitation, Pak Heru, we need to stop. But again, I would like to thank you for the very insightful and also very promising approach that you just present to us. And all of us knows that we really need the geothermal energy. At least in the future, we have the energy transition. We have a target for the net zero in Indonesia 2060. So we really rely on geothermal. And again, thank you so much, and please give applause again to Pak Heru. And I think from the committee, I would like to invite the chairman, Mas Ivan, to have a memento for you. Okay, please give applause again, one more.
Thank you to Pak Heru for the presentation, also to Pak Calvin to lead these sessions. And now we have the first technical sessions, oral presentations discussing the geothermal engineering aspect that will be moderated by Pak Miftah Hidayat. To Pak Miftah, please come to the stage.
Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera bagi kita semua. Salam Om Swastiastu, Namo Buddhaya, dan salam kebajikan. Good morning, distinguished guest speakers, presenter, and all other participants attend the 7th the International Conference on Geoscience and Earth Resource Engineering. This year, the theme is Synergy in Geoscience and Engineering, Pathways Towards Sustainable Earth Resource Development and Disaster Mitigations. We will now begin the technical sessions on geothermal engineering. For each presentations, the allocated time will be 12 minutes, followed by 3 minutes Q&A sessions, very brief. I kindly ask all the presenters to keep in mind that the time is limited, so we can proceed smoothly according to the schedule. So without further ado, it is my pleasure to invite our presenters to the stage to deliver presentations. The title of the presentation is Low Frequency Passive Seismic Methods on Geothermal Area, Part 1, 94 Key Field. Please welcome to the stage and give the round of applause for the presenter.
Cek. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Thank you for the opportunity. My name is Taufik. In this day, I will present our study about the low frequency passive seismic method, or we call it LFPS method, in geothermal area, part 1 in 94 field. In this presentation, I will separate about the content. The first is introduction, second is theory about the LFPS, third is result and discussion, and fourth is conclusion. The first is the LFPS, or low frequency passive seismic, is a geophysical method that utilizes low frequency passive seismic wave to describe inhomogeneity layer beneath the Earth's surface. So, based on the Dengers 2003 conducted observation using a seismometer to record ambient noise to the surface in the low frequency 1 until 5 Hz with the experience in a signal amplification phenomenon. And this phenomenon was analyzed due to the resonances of the wave propagating in the hydrocarbon reservoir. The illustration of the propagation or phenomenon is described from the figure inside. And then empirically, the LFPS can be duplicated in the field. This Kazantsev 2017 conducted to LFPS method analysis for exploration in the Muara Laboh geothermal field, where the high enthalpy steam saturated reservoir provide significant anomalous response to the vertical to horizontal atau H per V ratio to amplitude attribute. So based in this reference, we trying to apply or duplicate this method at LFPS to other geothermal field in our area. So, what about the theoretical about the LFPS? This is the Holzner 2007 described the method based of the principle of the nonlinear properties of fluid system in a porous medium. The reservoir is said to act the natural converter in the frequency from high to low Earth signal spectrum, because the reservoir is view a multi-fluid system in the porous medium. That the nonlinear entrancement characteristic, the illustration from the porous medium resonances is follow in the side of the description. So based on this, about the signal polarization or signal analysis, signal polarization is one of analysis performed. That time, series data to determine the direction of the arrival and movement of the recorded signal. So based on Jukervik 1988 and Sanger 2009, is introduce the calculation technique to analyze the earthquake signal polarization by solving the last square covariant matrix in the three measure signal component. First is azimuth, second is incident angle, or we can call it the dip. Third is planarity, and fourth is rectilinearity. So after that, we analyze the signal polarization. We call the fast Fourier transform to process the transforming data from the time to spatial domain into the continuous frequency domain. This is from the equation, the FFT process. So in this case, we using the Geobit C100 C100 borehole seismometer, apply into 120 point with 120 minutes of the data acquisition, and we get several 120. We calculate, we analyze in the quality control data, and only process the best, the excellent and good quality data is totally in 94 data, and we process it into our software in Pertamina. Is called it Pertare. Pertare is Pertamina software to process passive seismic data such as micro earthquake, MAQ, attenuance, Q, tomography, and low frequency passive seismic. And this study, we processing a flow chart. First is waveform, and then we cutting, the trend and windowing, rectilinearity and planarity, and we get the fast Fourier transform to get the power spectral density. And in this part, we classified into the VH ratio and amplitude and frequency like PSDN, E, and Z. Then we process the result of the area, 94 point. We selected in this case with illustration from the processing with Pertare software. First is the trend and bandpass processing. We use 1 until 7 Hz in this case, apply to all data. And then we windowing view in station key 72. We classify only the ambient noise section. We cut the peak signal in this section. And then the first polarization analysis based on Sanger 2009 is very difficult to have good quality like a Sanger 2009, but we in other field we testing to LIVS method. We have one of illustration with a Sanger 2009 is the best quality or best correlation with theoretical. This is with deep is larger than 60 degree, and azimuth randomly is from the random source, and rectilinearity and planarity larger than 0.5 or 50%. Then after that we do the FFT process to get the power spectral density, and we picking the frequency with a PSDZ with 343 Hz and PSDN, and E with 1.7 Hz. And this case in this point in Q038, we get the VH ratio is 1.5. So the result from the all point we processing, we get the map distribution of the result. The first is frequency Z distribute map, in the right, and the central is amplitude Z, VH, and frequency and amplitude VH in the right. So based on this data, we have a conclusion about the fluid on the reservoir in the geothermal. We have we show about the high amplitude and a low frequency in this area. Okay. After we trying to implement this LFS method to other geothermal field, after Muara Labo, we get the conclusion in the first area in our area. As the first is with 120 point. If we refer about the Sanger 2000, and then it's very difficult to get the same hypothesis about the lab testing in the field testing. So we only selected the excellent point with a 94 point and 94 point to be next processes. Second is we have a high frequency with 5 until 7 Hz values dominated in central and eastern area, and low frequency value in 1 until 3 Hz value dominated in the northwest and southeast research area. It's refer on the fluid on the reservoir, geothermal reservoir area. So high VH frequency values with 4 until 6 Hz were concentrated in two parts of the research area, namely the central to the west and central to the east. And in the south is refer about the distribution of the fluid in the geothermal reserve area. So about this result from the LFPS in one area, we trying to apply again to validate it, first hypothesis in the LFPS trying in the geothermal area, because this LFS actually show in the oil and gas result to determine the oil and gas fluid pathway. Okay, this is our reference to get the next result.
Thank you very much, Mr. Stovix. Please have a seat. Next is to me. I would like to open a Q&A sessions, maximum 2 questions, because we have a time limitation at the moment. Any questions so far? If you allowed me to do. Interestingly, that in the presentations, that the low frequency range is between 1 to 5 Hertz. But in this study, the conclusions say that the frequency range is between 1 to 7, so there is a shift at the typical a bit high frequency from 5 to 7. So what's happening? Is it something to the tools or possibly the interpretation? I don't know, possibly. Thank you very much.
Okay, thank you. Based on the oil and gas case study in the previous research on the oil and gas, we get the 1 until 5 Hertz based on the reference study like Dengel, Holzner, and Sanger. We call it in the oil and gas fluid pathway, we call it a 1 until 5 Hertz. So based on this value, we trying to apply to geothermal research area, how the range if we apply in the geothermal research area. So based on the first hypothesis in the area, in one area, we get the conclusion 1 until 7 Hertz. So based on this range, we trying to apply in the second geothermal area to validate it, the first hypothesis in this case. So after this, if we get the same frequency value, actually we get the conclusion in oil and gas and geothermal have a same frequency to describe about the fluid pathway about the geothermal reservoir.
Okay, so it's still under ongoing for the next research then. So we hope you can join us next year then to present the next result of your research.
Okay.
Thank you, Mr. Stoffik. I'm sorry that I have to cut this session because the time of limitations. I would like to invite all of the participants to give a round of applause to our presenters. Thank you very much. And thank you for your time, Mr. Stoffik. Before you return to your seat, there is a certificate from the chairman from the committee. Thank you, Mr. Stoffik. So it should be two presenters in the sessions, but due to current situations, the second presenter, the committee hasn't received any confirmations until now. So to honor his contributions to this conference, I would like to characteristic of micro earthquakes and fluid flow direction in Dieng geothermal field Indonesia. So that's all. We conclude all of this technical session on geothermal engineering. So let us now take short breaks and proceed to the next plenary sessions. Thanks again, and that's all from me. So I will return the floor to the MC. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much for Pak Mitah to lead these sessions. And ladies and gentlemen, we are now about to begin the second plenary sessions discussing about the petroleum engineering aspect that will be delivered by Bapak Muhammad Ali Ahmadi and be moderated by Bapak Calvin Lumbangal. To Bapak Calvin, we invite you to come to the stage. Mau coffee break dulu aja atau Mas atau Mas Miftah aja? Okay, while waiting for the moderator to come, please, to all the participants can enjoy some meal and a little light meal and coffee break at the back, but please directly come back to your seat. Thank you. lagi sih Mas? and gentlemen, we are now moving to the next second plenary sessions discussing about petroleum engineering aspect that will be delivered by Bapak Muhammad Ali Ahmadi and be moderated by Bapak Calvin Lumban Gaul. To Bapak Calvin, please come to the stage.
Okay, good morning again and welcome back to the fifth or the sixth plenary session for today. And today we have a presenter, Dr. Muhammad Ali Ahmadi, PhD, PN. He is a assistant professor now in Sharif University of Technology in Iran. And I would like to introduce Dr. Ahmadi, our current presenter today. So he received his bachelor in 2010 in petroleum engineering from Petroleum University of Technology, as well as the Master of Science in Petroleum Engineering from the same university, Petroleum University of Technology, in 2012. And he received a Master of Engineering in Oil and Gas Engineering from Memorial University of Newfoundland in 2018. And Dr. Ahmadi received his PhD in Chemical and Petroleum Engineering from University of Calgary. And Dr. Ahmadi has already a long working experience, start from 2020 as a data scientist in PetroChina Canada company till 2025, and from 2025 till now he's a assistant professor in Sharif University of Technology. So today we will hear or listen to the presentation from Dr. Ahmadi, and I would like to invite Dr. Ahmadi to the stage. Please give applause. So, Dr. Ahmadi, I think we can start now. The stage is yours.
Thank you so much. Hello, everyone. This is Mohammed Ali Ahmadi. It's truly an honor, and I'm deeply humbled to be invited at the ICGERE 2025 here in beautiful city of Bandung. So what I'm about to do today is actually give you some touch on how we can take advantage of the physics-informed artificial intelligence and machine learning to come up with solutions towards a more sustainable oil and gas industry. So as you can see in this graph, what we have on the left-hand side of the graph, that's today's standing of our energy industry. So nowadays we have lots of actually refineries, petrochemicals, and all those parts related to oil and gas that helps us and feeds us the energy demand that we have. But on the right-hand side of the graph, what we have is actually what we would like to have in the future. But as you can see, there is a transition between the colors. So what does it mean? It means that we have to actually bridge the gap. So the sustainability bridges the gap. In other words, there is no hard switch to turn the oil and gas off right now or probably in the future. So we have some concerns, okay? But the solution is actually addressing those concerns with the new type of technologies to actually, because we have the climate's imperative, so we have the carbon emission, we have to address that one. we cannot turn off the actually oil and gas. So, same as other problems, every changes actually come from the necessity. So the necessity today that we have is come from the climate change, the carbon emission from the industry, but we need to come up with new solutions. So the solutions that we have right now is based on the pure physics, okay? But the pure physics actually come with some limitation because we have to actually make some assumptions to do the modeling stuff, especially in petroleum engineering. We do the numerical simulation, numerical modeling. So we have to actually do some sort of assumptions to do the modeling. So those assumptions actually creates some sort of uncertainty in our modeling. We have to address that one. As well as due to the evolution of the industry, and not only the evolution of the industry, the evolution of the sensor technology, we got lots of data from the field. We got lots of data from different sources. So by embedding the physics into the data, we can come up with the physics-informed, data-driven modeling that actually comes with two advantages. The first one is our results will be physics grounded. At the same time, it's so adaptable because data by itself, we are not able to capture all the complex relationship between the data by themselves. So we can only do things based on the understanding of the physics that we know, okay? But if we combine them together, we probably can come up with the better solutions. And that solutions actually gives us the leverage to have a smarter decisions, probably close to optimum version of the solution. So just give you a kind of visual comparison between the pure physics-based modeling and the pure data-driven modeling. So on the left, as you can see, for the pure physics-based modeling, we used to use the governing equations, whether it's the thermodynamics, whether, for example, in petroleum engineering, Darcy equation, conservation of mass and energy, or rock physics, whatever it is. So it's so cool because it gives the upper hand for actually interpret the outputs based on changing the inputs. But at the same time, the limitation is it's computationally extensive to do it, and also it's very uncertain in lots of conditions. But on the other hand, for the pure data-driven modeling, what we have, we can take advantage of the machine learning and artificial intelligence nowadays to capture the nonlinear complex relationship between the data. But the thing is, we cannot actually understand what's going on inside the pure data-driven model. That's why we call them black box modeling, okay? So in some cases, they are prone to overfitting, and it means that during the development, it's very good in terms of accuracy and precision, but in terms of the validation phase, probably we get some wrong results as well. And not only that, also in terms of the physics, we don't have physics grounded results. So what I would like to present here is actually is the interface between the physics driven and the data driven models, and take advantage the both part of the modeling itself. So with the aim of that one, then we are able to come up with the new type of modeling probably. Sometimes we are able to embed physics into the problem, into the data-driven model. Sometimes we are not able to do it. So I have a couple of case studies that I've done so far. So the first case study is actually for the prediction of the wettability for the geostorage. So whether it's the carbon dioxide or the methane or hydrogen. So same as all the pure data-driven model, it comes with the data processing and preparation. So we do the same here. And for the model development part, it's the first time ever that we use the transformer with attention mechanism. So the transformer is the actually golden key nowadays because it's usually used in the natural language processing. So you see it as a fundamental in lots of the NLP, natural language processing tools today, and invented by Google DeepMind. So another model that I've used was the extreme gradient boosting. We call it XGBoost, and another one was the random forest based on the decision making. So, and then we had to compare the performances. So the only, one of the main actually factors that control the interfacial flow inside the reservoir, one of them is the wettability of the reservoir. Another is actually interfacial tension. So for the wettability part, based on the data that we had, with the gas composition, with the thermodynamic condition that we had, and with the brine ionic strength that we got from the literature, we came up to the new solution, how we can predict the wettability, because if we understand wettability very well, then in terms of the selecting the geostorage site, we would do it much, much better. And not only that, we also consider the hysteresis effect in terms of the wettability, because we are able to measure the advancing contact angle and receding contact angle, because it helps us to better understand if, for example, we are talking about the hydrogen storage. If we understand the hysteresis correctly, then we are able to do the hydrogen storage as a source of energy storage very well, because one time we want to inject hydrogen into the reservoir as a big storage tank for us, and another time we want to recover that hydrogen from the ground. So in terms of the recovery factor, one of the key things is the receding contact angle. But for the storage capacity, the key thing is advancing contact angle. So for that purpose, actually, as you can see, the left top corner plot presents the advancing contact angle based on the nature of the gas that we use, whether it's the hydrogen, whether it's the carbon dioxide for the carbon storage, or for the methane. Actually, in Iran, we have two ginormous reservoirs that we use as a storage actually facility. During the summertime, we inject methane on the ground, and during the winter, we actually produce that one to help us to mitigate the gas demand. So for the right plot on the top, as you can see, that's for the receding contact angle. So the model that we developed actually could predict both of them at the same time. So it gives us the leverage during the modeling, during, for example, the numerical modeling or simulation, the upper hand, because we have both advancing and receding contact angle at the same time. And in terms of the uncertainty, we compare the output of each model, and as you can see, the error bar on the bottom left corner plot, that's the correlation of determination as well as the RMSE, root mean square error, between the predicted value based on our models and the actual values that we got from the experimental data. And as you can see, for the transformer, the error bar is much, much lower than the pure data-driven XGBoost or random forest. So in terms of the physics embedding in this situation, we could only able to introduce the very simple concept that the contact angle actually varies between 0 all the way to 180 degrees. So that's the only physical constraints that actually we put into the place in this modeling. And not only that, we also did some sort of uncertainty analysis based on the quantile analysis for the outputs, so that the coverage of the prediction interval, 90%, the coverage that the actually diagonal line, if all the data close to that line, it means that all the predicted values fall into the 90% predicted interval. As you can see, consistently, Transformer did a great job in terms of catching up with the predicted interval, but for the XGBoost or random forest, actually sometimes they are overestimated, sometimes they are underestimated, the outputs. So that's one of the case studies that really helpful in terms of the geostorage. And in terms of the residual heat map, what does that mean is actually the error versus the value versus the predicted value of the advancing and receding contact angles. So as you can see, if you have the error bar, if you see the error bar on the right side of each plot, you can see the much brighter the point means that the larger the error is. So again, as you can see, for the transformer, for both actually advancing in this receding contact angles, we got the lower error, and they're so close to each other. So it means that in terms of the predictive power, we have a very good confidence about the output results. And the next case study is actually dedicated to the hydrogen system for actually underground hydrogen storage. So as I told you, one of the key parameters to consider for the geostorage was the wettability. Another one is the interfacial tension. So based on the data that we had, we got the thermodynamic, we got the composition of the gas, because sometimes we have the cushion gas, we call it the blanket gas, whether it's the carbon dioxide or other type of gas, and also the salinity. Based on the physics of the problem, we came up with actually the physical constraints to embed into actually our data set. So based on the experimental observations, most of the time we see the experimental outputs. Based on the experimental observations, the main parameter that directly affect the interfacial tension between the hydrogen and brine is the temperature. And also at the same time, another parameter that has some sort of effect, but it's not that much significant when it comes to temperature, is pressure. We didn't ignore that one. So for that reason, we came up with this constraint that actually the gradients of the temperature as a baseline with the scaling factor to actually to cancel it out based on the gradients of the interfacial tension versus pressure. So with the aim of that one, we ended up having this type of loss function that we want to reduce. So that's the whole story of the physics-informed actually modeling. And in terms of the results, as you can see, the top left, oops, sorry for that. The top left, I'm just waiting for that one. Yep. The top left plot, it shows the IFT in terms of the variation versus the temperature and the pressure as a surface plot. So the darker the color is, the lower the interfacial tension we have. So beside that one is actually, it shows the uncertainty in terms of the standard deviation. So as you can see, the more bluish we have, the almost zero uncertainty that we have. So it shows us, in other words, it shows us in which area we should take care of using such a model. So it's beautiful because in terms of the engineering application, it's not just only predictive tool, it gives you upper hand with uncertainty. It gives you better understanding when you should use this model, when you should actually consider some sort of limitation or uncertainty to the outputs of the model. And also we, based on the contour map, upper right plot, we were able to create a contour map for the interfacial tension based on the temperature and pressure. So we were able to actually find the regime of IFT that we were dealing with. And in terms of the actually physical loss that I showed you, the physical constraint that we came up earlier with, you can see the bottom left plot, the darker, actually the dark black shows the near or close to zero loss. So again, you can see at a special range of thermodynamic condition, you see some sort of loss or consideration. So if you fall into that specific thermodynamic conditions, then you have to consider the limitation of the output and you have to consider the uncertainty. And in terms of the importance of the inputs into the modeling, we use the Shapley additive explanation that introduced by a Nobel Prize winner in 2012, actually for the SHAP. It gives us better understanding the contribution of each feature in our modeling. So as you can see, the highest contributor in our modeling was the temperature, because the higher the value of the shaft value, as the larger the contributor, the contribution is. And the lowest one was actually the pressure. So it aligns perfectly with what we observed during the experimental. So another case study that probably you may like it is using the physics-informed machine learning for predicting the wax deposition, because we have lots of flow assurance problems in oil and gas industry. So to address that one, we had a bunch of data, thermodynamic condition, as well as the composition of the crude oil that we have. But based on the understanding that we had from the problem, beforehand, we started to introduce and engineer 2 new features. So the first one was actually, we call it the weighted average carbon number. What does that mean? Based on the weight fraction of each fraction cut of the oil. So for example, if we have a fraction of C1 all the way to C3, the carbon number is the is the median carbon value is 2, for example. And the carbon number for the cuts of C3 all the way to C5 is 4. And based on the weight fraction, we came up, because we have the weight fraction, we have the actually compositional analysis of the crude oil, we are able to calculate that feature as well. And not only that, based on the physical observation, the literature told us the fraction of the C16 plus is a major player for the wax deposition. So we came up with the idea to translate it to the feature that we can input into our model to have a better, better understanding of the problem in terms of the machine learning itself. So we came up with the LCHR, that we call it long chain hydrocarbon ratio. That's a ratio between the C16 plus over the fraction of the C1 all the way to C15. That's beforehand of introducing the physical constraints to our model. But based on, again, understanding of the problem, that by increasing the temperature, the wax deposition should be decreased. So to introduce that one, we came up with 2 types of physical and monotonicity loss functions to our model that actually creates a very smooth and penalize the model if it do the opposite. I mean, by increasing the temperature, the output should be decreased. But if the model predicted in a other way, and by increasing the temperature, the wax deposition increase, the output, the model will be penalized based on that loss function. So that's the whole story for developing such a model. And as you can see, we developed again with the random forest, XGBoost, and physics informed, in this case, neural network. But the thing is, sometimes the combination of the physics and the data, because of our limited knowledge about the physics of the problem, may actually ruin the output of the model. So in this case especially, that I put it intentionally in my presentation to show how critical it is to understand the physics and at the same time the data itself. So the XGBoost performed actually very well, superior than the physics informed. Why? Because the problem with the physics informed neural network in this case was the neural network couldn't understand the weight of the data loss and the weight of the physics loss. So it tries to find a balance between these 2 losses, but it couldn't was successful enough to pass the performance that we could get from the XGBoost. On the top, you see the scatter plot along with the error analysis on both X and Y axis. And the bottom plots actually shows the 2 two major components for each model as a 3D surface modeling. And as you can see, the physics-informed neural network couldn't understand the phase transition because it's really critical in terms of the wax. The nature of the wax is 100% different than the nature of the asphaltene. So for the wax, it's a phase transition phenomenon. So it couldn't capture that one. So it actually, one of our future research would be looking to the problem, deep dive, and find a better physical constraints to the model to make it a better actually predictive model. But compared to the random forest, it performed better than the random forest, but it still needs some sort of actually massage in terms of the modeling to get that type of performance. And then the last case study, I want to disclose it. It's the previous case studies already published. The first two published in the International Journal of Hydrogen Energy, as you can see at the bottom of the presentation. That was the credit for my publication. And the third one published in the Physics of Fluids, but this one is not published yet. So that's under review. So hopefully, fingers crossed, in the near future, we get the acceptance of it. So one of the main actually parameters in reservoir engineering is understanding the relative permeability curves. So in this case, we actually analyze more than a couple of thousand samples around the world, not specific to the region, around the world. So we came up with the physics-informed transformer model, first time ever, to create a predictive model that helps us to actually to have a better prediction with consideration of uncertainty. So because we use the transformer, we had the static feature and the dynamic one. So we put the static feature that, for example, that's the endpoint saturations, the wettability, the permeability, or petrophysics of porosity. We put into the encoder, and we actually input the dynamic feature, that's the saturation of the water, into the conditional network. So the conditional network, the encoder actually what it does, it finds the complex relationship between the features that we cannot see it, and then with the mapped and embedded that features into the neural network. Afterwards, we give the output of the conditional network which merges the static and dynamic features together. We give it to the decoder, and the decoder predicts the water and oil relative permeability curves. But we put some physical constraints based on our understanding of the problem. It's so easy. The first one is we know that the water relative permeability should be increased when we increase the saturation of the water. And again, exactly the same for the oil relative permeability. Beside those ones, we have the endpoint constraints. At the endpoint, at the critical points, the relative permeabilities should be 0. Okay? That's two constraints that we put into place into our modeling. And I'll show you how powerful it is. So in terms of the output, as you can see, probably in a couple of seconds, So I tried to show on the actually left plots, the scatter plot, based on the lithology that we had, because the lithology was one of our input features that was static because we are not able to change it. It is what it is. So based on the lithology for both water and oil relative permeability, you can see we got a reasonable output. And the top right corner plot shows the error density. What actually, what does it mean? It means that if we see the frequency of errors close to 0, it means that our predictive model actually was able to perform very well because we got errors close to 0. And in terms of the feature importance, the bottom plot on the right side, you can see the most important parameter in our modeling was the water saturation, as well as the wettability and the critical points, endpoint saturations. So these features are aligned with the physical understanding based on the experimental observation that we have. And I compared the outputs with the well-known correlations that we use in reservoir simulation. And you can see how awful they are. I'm so sorry for that one, because in terms of the performance, probably in a couple of seconds. Here we go. So I plotted the Curry, Brooks Curry, and LET as the most let's say useful correlations that we use in reservoir simulation and numerical simulation. And you can see that they are awful in terms of the prediction because they developed based on lots of assumptions. As I told you at the beginning, with the assumptions, we actually will limit ourselves. But with the data-driven, why they are adaptable, they can understand what we can't understand. So they can capture the complex relationship between the features that we are not able to do so. So based on that, as you can see, the mean square error and also the coefficient of determination for these three correlations that we use in reservoir simulation, it's not actually acceptable. We should think of actually new type of modeling to correct ourselves, to improve the accuracy and precision. So for that kind of case study, I came up with this kind of loop. I call it physics-informed AI loop. It starts with the data, whether it's field data or it's from the Markers dynamic simulations or whatever the data source is, it doesn't matter. And by understanding the physics behind the problem and try to embed those physics, whether it's the thermodynamic understanding, whether it's the fluid flow physics or rock mechanics, and with the AI engine, we are able to actually create a solution that gives us the upper hand, which is insight. And based on those insights, we are able to actually perform much informed decisions and probably much smarter decisions, which helps us to address the sustainability concerns in our industry. And in terms of the, let's say, conclusions based on those case studies, as you can see, it can combine both the physics and the adaptability of the data that we use. It can be applied from all the way from the Markov scale all the way to the field scale, and also it creates efficiency, precision and accuracy that we want to have for having a sustainable oil and gas. And also, it's not limited to oil and gas. We can apply it in a multidisciplinary and interdisciplinary, actually, industries. And that's the final quote. The data is alone is not enough, and the physics alone is not enough though. So the future of the sustainable oil and gas industry lies on the fusion of the physics, data, and insight, which transforms the challenges into the opportunity for a resilient, low-carbon energy future. And thank you so much for your attention.
So much. Please give applause. Okay, thank you so much for the very interesting. So now we are in the question and discussion session. So please, if you have any question. Not yet, so maybe I will like. Oh, okay. Yeah, please.
Check. Okay, thank you. First of all, let me introduce myself. My name is Daniel. I'm currently a graduate student here at Petroleum Engineering at Bandung Institute of Technology, and I will ask you about one thing, because in this presentation, what I got from this presentation is that we can use machine learning with the constraints of physics. And one of my questions that comes to my mind is, what is the strength and the weakness of this type of machine learning compared to the commercial software that is currently being used in all of the petroleum industry? Thank you.
Okay, please. Okay.
Thank you so much for your question. So the upper hand of the machine learning method, so as I told you, all of the simulation software that we use in petroleum industry suffers from the limitation of the understanding of the problem, because all those simulation softwares, we are not able to solve the problem analytically, so we have to make some sort of assumptions to actually do the modeling numerically. So we have lots of uncertainty during the modeling in petroleum engineering. As I told you, it's very uncertain during the usage for the, let's say, problems that you assume it or oversimplify it during your modeling. But when you use the real data, it tells you what you wouldn't know beforehand. So what I mean by that, it means actually based on the pattern inside the data that we are not able to capture, but the machine learning models can capture it, we have a much better adaptability and also lower uncertainty compared to the commercial softwares that we use. So that's all in all is uncertainty and adaptability that we can get. And also they are super fast. They are super fast. It's not even compatible in terms of the computational capacity that you need for doing the numerical simulation for a full field, but it's not even comparable what you can do with the AI and machine learning when it comes to data analysis and get the insight from the data. Is it part of your answer?
Yes, it answered it beautifully. Thank you.
Thank you. Is there any other question? Yes, please.
Okay, first of all, thank you very much for Mr. Ali. And I just wanted to asking you a simple question about your And you highlighted in your presentation about the fusion with physics and AI, especially in how to be sustainable in oil and gas industry. And my question is, what the practical implication of the case of your study result, and how can this can be finding to be applied in the field to improve the efficiency, to reduce the risks, and optimize the operation, especially in oil and gas industry? Maybe that's just I wanted to asking to you. Thank you.
Okay, thank you. If I got your question correctly, you mean what is the implication of those case study? So as I told you, for hydrogen storage or geo storage, you have to understand the wettability. So during the numerical simulation, you should know the wettability, the interfacial tension, because it really actually affects the output of your modeling. So by coupling this kind of modeling, machine learning and AI based, to the proxy modeling, not a full field reservoir simulation, we are able to actually do things much faster and with a much lower uncertainty in terms of the decision making. So the thing is, during the numerical simulation, you have to assume, for example, a specific values for interfacial tension or wettability. But wettability, you can get it dynamically based on the developed model. It's not a single point, it's not a single prediction. So you can get the wide range of wettability map that we actually don't have it in the commercial numerical simulator. And not only that, you can have a dynamic interfacial tension map for your reservoir. That's one kind of examples. And not only that, with the kind of physics informed, we were able to actually during my work, I'm not disclose the name of the company, so we were able to actually predict the failure and the lifespan, the remaining useful life of the ESP pumps inside the well, and it could actually create $200 million gross profit for the company just in 1 year. So that's the beauty of the physics, the data-informed decision making. So I hope that's a part of your that's a part of the answer of your question.
Okay. Yeah. Unfortunately, of course, because we have also the time limitation. Amadi, thank you so much. Very interesting topic. And yeah, for those of you who are not really familiar with the topic, I mean, this kind of wettability prediction, relative permeability prediction, interfacial tension for CCS, for gas storage or hydrogen storage is really we have a very limited data, let's say something like that. Yeah, if we have very limited data, so in application, if we have these tools, it will help us a lot, yeah, in the future. So again, thank you and very interesting. Yeah.
Thank you so much.
And I think I would like to invite the chairman of the conference, Mr. Ivan. We have a memento for you. Please, you can stand in here. Thank you so much.
Thank you for such an insightful speech from Bapak Muhammad Ali and for Bapak Calvin to lead the previous sessions. Now we are moving to the next second technical session, oral presentation from Petroleum Engineering, which will be moderated by Bapak Miftah Hidayat. To Bapak Miftah, please come to the stage.
Okay, so we continue the technical sessions. Let me start with good morning to good afternoon. I'm not sure it's still in the morning or not. Rest, relax a bit. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera bagi kita semua. Shalom, Om Swasti, Namo Buddhaya, dan salam kebajikan. We will now begin the technical presentation sessions on petroleum engineering. For the each presentations, the allocated time will be 12 minutes, followed by a brief 5 minutes Q&A sessions. I kindly ask all the presenters and the participants to keep the time in mind so we can proceed smoothly according to the schedules. So without further ado, it is my pleasure to invite our first presenters to the stage to deliver the presentation with the title, A New Method of Drilling Bit Running Evaluations. The presenter would be Professor Bapak Punar Marbun from Petroleum Engineering ITB. Please give a round of applause.
Thank you very much, Mr. Miftah Hidayat, PhD. So, first of all, I would like to express my gratitude to Mr. Ivan Kurnia, PhD, the Chief of Committee of this wonderful conference, and also the whole team. And the next, I have seen also our Dean, our lovely Dean, and Vice Dean of Resources, and also for all of our faculty fellows and distinguished ladies and gentlemen. So, yesterday we heard a presentation from Mr. Professor Taufan Marhendrayana as Deputy of Exploitation of Special Task Force for Upstream Oil and Gas Business Activities, or as Kakamigas. And actually, we Indonesians are facing big challenges. Our oil production is in deficit, but our gas production is slightly better. And as one of the supporting components of the national oil and gas industry, we from campus can contribute as well as possible. So hopefully, this tiny research can be a speck of good things that can be a glimmer of hope for the future. So this is a new developed method of drill bit running evaluation based on cost per foot and hydraulics analysis. I would like to present on behalf of our team. We can see here Mr. Reza Aditya, the second one. He is the drilling manager of PHR, or Pertamina Hulu Rokan, Region 4, and supported by us, ITB, myself, and also especially two fresh graduated, Gois Fatur, fresh graduated petroleum engineer, class of 2020, and last but not least, Feril Pratama, also fresh graduated of class 2020. So, distinguished ladies and gentlemen, we have heard so many terminology from yesterday and today. For example, what we have already heard about machine learning, big data, and so on. But as a matter of fact, we Indonesia is still suffering. We are not Canada, we are not Germany, or even China, with the highest level of the quality and quantity of assurance. How about data, especially in the drilling engineering? We know exactly that wellbore is a part of component from the whole giant oil and gas industry. From the borehole, we can produce from subsurface to the subsurface or vice versa. From the borehole, we can inject something such a fluid from the surface to the subsurface. But in the reality, we can see from the data, on the fact, but this is the reality, even though we have starting our drilling engineering history since 1870. And in this field, Prabu Muni field, we have started to conduct a wellbore since 1895. We still are suffering with data collection and especially how to analyze it properly based on the standard which has been acclaimed as international value. So here we are. Two kinds of wellbores have been drilled with two kinds of rig capacity, and our task was to conduct the assessment and try to collect the data as many as possible so that such of support from ITB can be offered to the industry, especially for our national oil company, so that the drilling process can be accelerated, not only engineering-wise, but also based on economic. So here we are. We analyzed all of aspects. So we have discussed already that the commercial software which are available in the market, they are pretty high quality. It is very, very clear. But based on the use-friendly aspect, there are some kind of assumption has been used, and in special cases, especially at the field in Indonesia, where we still have lack of standardization, guideline, and so on, it is pretty hard how to analyze an appropriate assessment that can be compared apple to apple from one bore to the other well bore. So this is we are from where we just let's say well 1 and well 2. Both well is analyzed appropriate to the standard of IADC, International Association of Drilling Contractor. But the challenge is also, as a part of game, how to read the report, because the report system, especially by us in Indonesia, are still very, very hard and difficult to analyze from one to the others. So at the end of the day, we have finished all of the analysis, and here we are. This is such of method that has been conducted under the loop, cannot be carried out with software. No, not at all. Instead of software, we have to read every page of paper. We have to conduct the interview of every single engineer at the field so that we can carry out such of methodology which is very, very complex and need a high precise level. So I can skip this page. We can go directly to the reality for these two kind of wells. So distinguished ladies and gentlemen, we can see here especially of capacity of rig from the fourth line of the bottom. Two kind of wells have been carried out with 2D kind rig capacity. The first one by 1,000 horsepower and another one by 1,500 horsepower. So here we are, it is very clear, crystal clear, that the performance, the productive time, and all of kind of parameter can be clearly compared. Even if we have used the same bit size, the same bit type, polycrystalline diamond compact, even with the same code, 2:1, the quality of the wellbore is totally different. So, where was the problem? How can we use such of data for the next future so that we can accelerate the process of the drilling, starting from design, execution, analysis, and evaluation? Such of formula is well known since we are studying petroleum engineering in the third year. We know exactly about cost per foot. This is a classic formula, has been constructed since 1965, especially in the field of New Mexico, and we know exactly every single variable that is used in this formula. But we still have keep in our mind that such a formula has been developed in the United States of America, where everything is good controlled, where all of standardization has been announced and proved. How about us in Indonesia? One of the biggest problem is that we still have a high NPT, non-productive time. What is that? We always try to design a wellbore not only based on cost, but also based on time. We would like to achieve as high as possible effectiveness level and efficiency level. But we can see, as a matter of fact, from Sabang to Merauke, that NPT level of our drilling, not only by Pertamina, but also by BP, comparing also with ExxonMobil, we are still facing some problems with our high non-productive time. And of course, this influenced the quality of wellbore, and at the end of the day, all of the important parameters of oil and gas industry in our lovely land. So, what we have done? We have done, all of the parameters have been corrected based on the reality. Here we are. This is one example how we compare the measure depth as the function of rate of penetration at the sum structure, at the sum lithostratigraphy, at the same human resources. Every single factor is the same as it is. But we can see here that the rate of penetration, the level of quality is totally different. And the next one is the true vertical depth as the function of rate of penetration. So distinguished ladies and gentlemen, this is a phenomenon that cannot be ignored by us, especially in Prabu Muli. The next point also, last but not least, about the weight on bit, which cannot be controlled as smooth as possible, that actually we use in best practice in oil and gas industry. And direct to the point that we can see here, even with the highest quality and technology which appear in industry, we still have an issue with top drive system. Top drive is actually an old-fashioned technology. It's well known since 1970 or 80, but we can see here, for example, that non-productive time which occurred in Prabu Muli, even though since 100 more years with oil and gas industry, especially for drilling engineering, the non-productive time is still, let's say, superb. And this one, you can see here, even with the better, higher capacity of rig, the well one with light blue is bigger than well two with dark blue. Why could on earth such a phenomenon can still be occurred with 100 more years tradition of oil and gas? That's why we were here to conduct the analysis properly, and after all, we can see here, for example, the hydraulics, one of the important point of drilling engineering that cannot always be identified and compared one to each other. That's why we tried to make a better program based on our ITB software so that the parameter of hydraulics can really be carried out based on the better way. And here we are, based on the result, that some appropriate point which can be improved in the near future. Here we are, this is the calculation that we have found out that the effectiveness and the efficiency level of every single well in the future should be more or less better calculated based on the appropriate reports, so that one can be compared to the others, especially the hydraulic analysis that's still a great issue in National Oil Company of Indonesia, Pertamina. So I do hope that such of tiny offering by us ITB can be little support so that the productive time can be increased in the future. Yeah, about the detailed recommendation, you can read quite in peace in our publication that proposed by especially for this conference. So I will not read one by one. And that's all. That is the end of our presentation. Thank you very much for your attention, and I can get back that to Mr. Mitfa Hidayat, PhD. Thank you very much.
Thank you very much, Pak Bonar, for the presentations, very insightful presentations. I would like to invite you to sit next to me for the Q&A sessions, Pak Bonar. So we now open the floor for the brief Q&A sessions. So all the participants who has question, please raise your hands and the committee will come to you to give the mic. Any questions from the participants? So to summarize the presentation and asking the questions, Pak Bonar. So I would like to ask, so what's the main factor that affect the NPT between these two wells? Because the comparison of the NPT is too high. I mean, like, it's very big. So what's the main factor, Pak Bonar? Could you please give us an insightful information about that.
Thank you very much. So, the cardinal challenge of us, especially in the drilling engineering of Indonesia, we have still lack of guidance, standard operating procedure, and such of line so that we can compare what we are able to comparing to the international standard. That is the cardinal point of us. And the second one, based on such condition, lack of standard operating procedure which is appropriate based on the international standard, we conduct a design, and especially the operation, the execution of our design is not always optimum. That is the second main problem, so that we sometimes do not know what we have to do and how to analyze so that we can improve and get the better result in the future. Why is it the problem? Because we know exactly that the exploration and the production activities from our first history has been conducted from many kind of industries country, for the likes of ARCO in ONWJ offshore Northwest Java, WMO by Codeco, South Korea company, BP in Papua, or ExxonMobil in Arun, and also now in Cepu. So they have their own standardization. And to be kind, it is pretty different, especially the standard operation procedure of European side comparing to the United States sites. And after all of this field have been finished with the contract and by government, get back to the Pertamina, our national oil company, it is pretty hard to continue the operation based on such of different kind of guideline. It is also one key point. So what we are conducting now from campus side, not only how to achieve an increasing of production, but also how to support the Pertamina to make the harmonization, to conduct the uniform of standardization, so that not only for the new wells, but also for the old wells, we still have hope for increasing the production can still be carried out. That is the answer, Mr. Miftah Hidayat.
Thank you, Pak Bonar, for the insightful information. So the current problem in our side is the lack of the standardizations regarding the guideline and operating procedure. Okay, any question from the participants? Apologies also to Pak Bonar due to our time limitations, and if there is no questions from the participant, I will now conclude the sessions for today. For these times, I would like to invite Pak Bonar to return to their seats, and please give round of applause to Pak Bonar. Terima kasih, Pak. So for the next sessions, I would like to invite the next presentations. The title of the presentation is The Flow Assurance and Production Efficiency Enhancements through Strategic Water Rate Optimization in Offshore Pipeline, a Krishna Cinta Pipeline Case Study Offshore Southeast Sumatra. So this presentation will be delivered online as the presenters cannot attend today conference. Could the committee please show the...
Yes, hello.
Yeah.
Yes.
Thank you, Mr. David.
I am here. Sorry, my name is Noval, Muhammad Noval Rizky.
Okay. Apologize for my mistake. So, Mr. Noval, so please present the presentations. The maximum time will be in 15 minutes, and then we follow by Q&A sessions. The floor is yours.
Okay, thank you. Good afternoon, everyone. My name is Mono Fariski, representative of the team, and today I'm pleased to present our study in improving production efficiency through strategic water rate optimization in offshore pipeline system. So this case study of the Krishna pipeline location in offshore Southeast Sumatra. Please next. Okay, so for the introduction, the flow assurance is a critical in offshore oil and gas operation, ensuring safe and continuous fluid transport from the reservoir to the storage facilities. One major challenge in multi-phase flow system is phase segregation, particularly in oil and gas, due to low flow velocities. And according to APA 14A, the minimum recommendation liquid velocity is 3 feet per second to avoid deposition and separation. And show in this diagram, the lower velocity leads to a stratigraph flow, resulting in oil accumulation and production loss. In contrast, higher velocities promote bubble and disperse flow, ensuring better mixing and transport. Okay, next. Okay, so for the field case overview, this case is located in offshore Southeast Sumatra field. 12-inch pipeline, nearly about 30 kilometer, connect 5 major production area to the central processing system. We encountered a mismatch in water cut between Krishna and Cinta platform. Indicate oil loss during transfer due to fluid segregation in the pipeline. Okay, next. So this slide show about the production monitoring in February 2025. The daily production monitoring show that the flow rate range between 22 and 24.5 kbfpd. However, the water cut at the Cinta platform was consistently higher than at Krishna. This discrepancy indicates oil water segregation, and the estimate daily oil loss peaked at 900 something BOPD, confirming inefficiently the pipeline transport. Okay, next. Okay, so we conclude with engineering study and simulation with one of software we know multi-phase dynamic software. So to better understand this issue, we built a model, and the results revealed that existing fluid velocity was only about 2 point something feet per second and below 3 feet per second threshold. This condition result in stratified wavy form and inefficient oil displacement. So we propose an optimized scenario by increase the flow rate to around 34 kbfpd and more. This will raise the fluid velocity above 3 feet per second, shifting the flow regime to mix or to disperse, and reducing oil hold up and mixing and minimize oil loss. Okay, next. Okay, so for the pilot test to the high rate flushing on February 24, 2025, we conduct a pilot test by reactive one of high capacity crude oil transfer. We known as COTPB, crude oil transfer pump B. The flow rate was increased to 35 kbfpd. The pipeline pressure rose from 120 to 200 psig, and the fluid temperature remains stable above the wax apparent temperature. And more importantly, water cut at Krishna decreased significantly, and oil delivery efficiency improved from an initial 8 kbopd to 10.8 kbopd, proving better displacement. Okay, next. Okay, so for the result, as shown in this graph, the pilot test delivered clear benefit. We observe strong press response. We can see as this graph, reducing BSV, or we know as water cut discrepancy, and improve alignment between wellhead and receiving platform. This result confirm that increased fluid velocity, enhance flow assurance, and production efficient. Okay, next. Okay, so for the continuous implementation reactivation, following the successful pilot, we continuous implementation from February to Maret, the activation of GeoTPB with 34 something kbfpd flow rate, with improvement of production. So the well test accuracy, or VBSW accuracy, is improved from 50 to over 75%. And water cut is decreased between Krishna and Cinta, and the Krishna flow rate increase. That indicates better oil replacement. Okay, so the conclusion and recommendation: maintains fluid velocity above APA, reverse APA 14A. The minimum of 3 feet per second is critical for mitigate oil loss and enhance flow assurance in multi-phase pipeline. Both simulation and field operation validates this strategy. We recommended for the boosting operation, or make the flow assurance strategy better in offshore pipeline, to encourage the pipeline in offshore to increase 3 feet per second at minimum boundary. Okay, next. Okay, that concludes our presentation. Thank you for your attention. I look forward for question and discussion. Thank you.
Thank you very much, Mr. Noval, for the presentations. I would like to invite the audience, the participant, if you have any questions, please raise your hand and the committee will come to you. Regarding the question, Mr. Noval, I have one question related to the presentations. What the trade-off should be? I mean, should be considered between increasing the flow velocity to mitigate the oil loss, like above 3 feet, above reference value from the APA, compared to the potential risks could be happen, such as erosions, corrosions, or even energy consumptions, something like that.
Okay. Hello, test.
Yes.
Okay. The purpose of the 3 feet per second it's the minimum velocity, but in APA 14A, the maximum velocity declared in that I think it is around 7 or 10 feet per second to mitigate the erosional. But thank you for that mention. So for the multi-phase flow, that's world recommendation operating between 3 until 10 feet per second. That's typically safe, but maybe the company must check again about the MAOP, maximum allowable pressure in the pipeline. So if the 3 feet per second makes the pipeline pressure above the MOP, the better solution is make it lower than 3 feet per second. I think that's for the question.
Okay, thank you very much, Mr. Naufal, for the answers. Any question from the participants? If not, thank you very much for your time and the presentation, Mr. Naufal. Now we are conclude these sessions, and thank you very much. And please give Mr. Naufal a round of applause for his times and his insightful presentations. And usually, I would like to say that I would ask the presenter to return for their seat, Mr. Naufal, but at the moment, I couldn't say that. I'm sorry. So thank you very much for your time. So we are moving on to the next presentations. So for the next presentation,
Okay, thank you.
I would like to invite the presenters of the title of the presentation is Analysis of Pore Pressure and Overpressure Mechanism in the R Field, ASRI Basin, and Feasibility Evaluation of the Tal-Akar Formations as Carbon Store Allocations. Please, the presenter come to the stage. Oh, yeah, please, yeah. Oh, I didn't see
Thank
it.
you. Check. Okay. Good afternoon, everyone. It is a pleasure to be here today. My name is Adinda Fadila from Geophysical Engineering Department, Institute Technology 10 November, Surabaya. And I'm the first author for this work. And I'm also collaborate with the several authors from the Geophysical Engineering Department, ITS, and also the PT Pertamina Hulu Energi OSES. And our works titled by Analysis of Pore Pressure and Overpressure Mechanism in the R Field ASRI Basin and the Feasibility Evaluation of the Tal-Akar Formation as a Carbon Storage Location. Okay. The research location at the ASRI Basin, that we know that the ASRI Basin is a big field that average oil production around 90,000 BOPD per day. And we know that the tectonic of the ASRI Basin is also stable. And why the ASRI Basin is a best candidate to implementing carbon storage, it is about the ASRI Basin is located as the transition of the located by the Sumatra and the Java. And the Sumatra, it's a system of the strike slip system with the manifestation by the Great Sumatra Fault, while the Java have a deep slip thrust fault with the manifestation with the volcanism. And when we see individually between the Sumatra or the Java, it cannot be discovering the really stable tectonic condition. to having implementation carbon storage location, while the Asri Basin is a best candidate to implementing this. And we know in the figure 1B, it is a Talangkar formation. That is, in the previous study, we know that the Talangkar formation has the lateral continuity and the porosity effective to having a storage of the carbon. And the depth of the TRF is also more than 800 meters, so it can be maintained, the carbon, to have a supercritical phase. And so we have two objects. It is drilling new wells, because the Asri Basin is also the large field. And the second one is the carbon storage. So the pore pressure is the parameters essential for the two objectives. So in this research, we would like to perform. The first one is 1D pore pressure profile, and the two is analysis of the mechanism of pressure, and the third is creating pore pressure distribution model. And at the previous study, we know that the Eaton method to calculate the pore pressure is also reliable to all of the mechanism analysis. And at the Asri Basin, we cannot discovering of the literature about the pore pressure, for the overpressure mechanism, so we perform in this research. And the third is a model-based inversion that we choose to be distribute our pore pressure. That the model-based inversion also take a log as a constraint and can give the lateral continuity. Okay, this is the research purpose. The one is the calculating the pore pressure profile. The second one is the determining overpressure mechanism, and the third is build a pore pressure seismic distribution with the post-stack model-based inversion. And the last is determining the feasibility of the Talangkar formation for the carbon storage. Okay, this is the data that we use. It is a final well report, 3D seismic data, seismic horizon, and a well profile. Also the log data and the pressure test like the ST, RFT, and MBT, and also Poisson ratio and the check shot. And the geochemics data mainly to have a conduct overpressure mechanism and well marker. Okay, this is the research workflow. It can be seen that more complex, so I will summarize at the next slide. Okay, so this is the methodology that we can see. One of the first one to have a conduct the pore pressure log is summarize the data from well report. After that, we have a Bethel correction, and the third is conduct the Miller density. The Miller density is a density at the shallower depths. After we have a fulfilled interval density, we can perform the overburden stress. After that, we can discriminate of the shell interval. So for the information, the pore pressure, it also can modeling just to at the shell interval, because the shell interval have low permeability, so the fluid can be escaped quickly and can be represent the really pressure at the bottom. And the next is NCT, or normal compaction trend. After that, we calculate the pore pressure using the Eaton and validate with the pressure test data, and we calculating again fracture pressure based on the pore pressure output and also the Poisson ratio value. After that, overpressure mechanism, it is mainly geochemical data. The first one is the plot of the log trend. It is a slowness, a DT, neutron porosity, and the density log by depth, and the data like the bottom hole temperature, a peak generation temperature, maturity index, mineralogy, and the clay mineral to have a ternary diagram, and the log cross plot between the sonic density and the porosity density. Okay, this is the methodology to have a distribute of the seismic per pressure. So it's actually have a flow like usually to having a seismic inversion post-stack, but the difference that we conduct is start at the well seismic tie, that the well seismic tie in this have performed 3 times for the VP and for VP shell and for VP normal compaction trend. After that, we also have an initial model. That the initial model have a 5 model between the acoustic impedance, density, hydrostatic pressure, overburden stress, and NCT. After we have a 5 model, we calculate with the trace method option to build the pore pressure distribution like this. And after that, we can slice this. Okay, the first result is a 1D pore pressure. We can know that the 7 wells is located at the different structural geology, and we know at the figure 8, the log pore pressure in SG unit or gradient unit. The blue curve is a pore pressure by dt or slowness log, but the red line, it is by resistivity logs, and the black color vertically down, it is a hydrostatic pressure that we know that when the pore pressure exits from the hydrostatic, it can be stated as overpressure. That from this picture, we can see that the overpressure is mainly occur at the lower section at this. In this case, it occurs in the lower Zelda, lower part Zelda, or LL Zelda to Vanuatu clastic interval. And the purple curve, it is about the fracture pressure, and we can see that from the 7 wells, the pore pressure does not reach the fracture pressure. And from the 1D pore pressure, we can know that the geological structure relatively affect of this value of pore pressure. Okay, next is about the overpressure mechanism analysis. The first one is the log data trend. So we can see about the normal pressure is occur at the top interval until the lower Zelda, that we know the normal is identified by the decreasing neutron porosity, increasing density, and also increasing slowness. Well, the opposite of the normal trend, it can be stated as a unloading mechanism. It can be identified at the lower Zelda to Vanuatu shell and interval approaching basement. And the loading mechanism can be identified at the stagnant or constant of the third log. After that, we also plot of the bottom hole temperature, that we know that the bottom hole temperature can be identified for unloading mechanism, that we know the unloading mechanism or the pure elite, it's around 120 degrees Celsius at an unloading mechanism. It's occur in Vanuatu clastic. And after that, we have a peak hydrocarbon maturation temperature that we know is a focus on the states that early mature and the peak mature. And after that, we know that the unloading mechanism is occur at the lower Zelda, Vanuatu shell, and Vanuatu clastic. And Vitrinate reflux stands as a parameter of the hydrocarbon maturation. It's also the same to have unloading mechanism analysis, and the result is begin at the lower Zelda, LL Zelda, and Vanuatu shell interval. And the mineralogy, the first one is for loading, but the value of the plot is not extreme, so we cannot to take the conclusion. the mineralogy plot for this is for the unloading mechanism. The same, it cannot be take a conclusion because the value is not really extreme like this. So we perform the ternary diagram to having validation of what the mechanism of pressure in this area, and the result is the data collected on the medium high kaolinite elite, low medium chloride, and very low smectite that indicates that the data is a alteration product, that the alteration product is also associated with the unloading mechanism. And the last one is the log cross plot. It is actually the multi-well cross plot. So the first one is the sonic density cross plot, and the second one is neutron porosity and density cross plot. And we know that the unloading, it can be identified when the data following the the elite line that colored by blue line, and we know that the unloading mechanism, it begins around 6,000 feet. Okay, this is the sensitivity analysis. The first one is about the acoustic impedance versus pore pressure log to conduct the correlation between them. So the difference between the third picture is about the depth color, gamma ray color, and the well name color, that we know that the correlation is just 0.51 is due to the combination of the pressure mechanism. So when the data is following the regression line, it is a normal pressure, but when the data is opposite with the regression line, it's about the abnormal pressure, and we know that the abnormal pressure is mainly occur at the R3 and R4, and the depth is above 10,000 feet. And after we perform of the seismic inversion pore pressure, we also can cross plot with the log pore pressure. So this is the log pore pressure cross plot and the pore pressure distribution, that we know that the correlation is 0.91. It is a high correlation, but we know that the data is also have a variation between the regression line. So it can be stated that the data at the lower part, mainly as the Vanuatu formation, as the source rock of this interval, it have a really abnormal pressure. Okay, this is the seismic pore pressure cross section. We know that the area between the R1 and R2, or the western flank, it has a higher pore pressure, while the compare between the R5, 6, and 7 in the northern flank. So in this seismic inversion of pore pressure distribution, we can state that the depth or the structural of the location is not related with the pore pressure value. And only R3 and R4 at the central basin, it has a high pore pressure extensively at the lower Zelda, LL Zelda to the basement. And this is the seismic pore pressure lateral slice based on the Talang Angkar formation horizon and the basement horizon. And we know that the sequence of the highest to lowest pore pressure is from the central area. So the central area is really have pore pressure value high, and also the western flank to northern flank, and the last is western crestal until the northern crestal. And the top formation Talang Angkar actually has normal pore pressure. So the Talang Angkar formation has the normal pore pressure, excepting the lower Zelda section. So for the carbon storage location, we have three parameters. That the first one, as I said before, that the Asri Basin have a stable tectonic rather than the basin at the Sumatra and the Java, and so it is a confirmed to basin location. And the second is reservoir depth, and the Talangkar formation has more 800 meters, so has maintained to carbon storage as a supercritical phase. And the third is a pressure regime, that we know that the Talangkar formation has a normal value accepting lower Zelda section. So the conclusion is the first one is the one vertical pore pressure have the Batu Raja formation as the upper section of this interval have the normal pore pressure, and the Talangkar formation is also have a normal pore pressure except lower Zelda approaching the Banuati shell interval, and the Banuati as a source rock in this interval has the highest pore pressure or experience overpressure. And the second is the mechanism dominant in this area is the unloading that occur at the lower Zelda to Banuati clastic interval, while the loading is also occur at the lower Zelda to lower Zelda and the interval approaching the basement low. And the third conclusion is from the 3D pore pressure distribution, we know that the highest pore pressure is concentrated at the central area or low part in this area. And the fourth is the Talangkar formation is suitable for the implementing carbon storage location, but we can more attention to the lower Zelda interval. So, because we have condition of pressure is found by well R3 and R4, and to avoid drilling event, injection failures, and carbon dioxide leaking, it is recommended to avoid the central area, and the maximum zone for injecting carbon is the lower Zelda, not reaching lower Zelda. Okay, thank you for your attention.
Thank you, Ms. Fadila, for this insightful presentations. Please have a seat here. We now open the floor for the Q&A sessions. All the participants, please raise your hand if you have any questions. Possibly I have one in me, but if there are any question from participants, if not, okay.
Okay, good afternoon everyone. My name is Alvaro Putra Ramadhani, serving as fourth year petroleum engineering student from Bandung Institute of Technology. I have one question for this topics that was interesting topic for me. The first one is, what is the main evidence of this analysis of the storage that can trap the carbon suitable for this carbon? What is the main evidence of this analysis?
So
thank you.
Okay, please answer.
Okay, thank you for the question. Actually, in the Asri Basin, now it's just study. So in the Asri Basin, until now, we don't have injection of the carbon storage. So the evidence of this feasibility of the Talang Akar formation as a carbon storage location, it's a limitation of our research. Like our research is really focused on the pore pressure. So the conclusion of the suitable or the feasibility of the Talang Akar is just the pore pressure. So the pore pressure in this area is the feasibility, but the reality that the trap of the carbon storage is also considering all of the parameters at the petroleum parameters like the flowing, the carbon and extra, it's our limitation like this.
Thank you. So just want to put it in the terms that the possibility of the Talang Akal formations that can be suitable for the CCS project is based on the pore pressure and upper pressure mechanisms. And to answer the question, the evidence that formations could hold the pore trapping mechanism is not been studied yet. Okay. So I think we now conclude the sessions. Thank you very much, Ms. Fadila, for the presentations. I would like to invite you to return for the seats, and we will begin proceed for the next presentations after 5 minutes. Okay, ladies and gentlemen, all the participants, speakers, and the guests, we will continue our technical sessions in the petroleum engineering. So, without further ado, I would like to invite the next presenters. The title of the presentation in History Mass-Driven Capillary Behavior Identifications of Microbubble CO2 Injection for Core Flooding Data. So, for the presenter, Mr. Egy Pratama, please come to the stage. The floor is yours.
Okay, thanks, Mr. Miftah, for the opportunity. So this segment is entitled History Image-Driven Capillary Behavior Identification of Microbubble CO2 Injection from Core Flooding Data. So the outlines for this presentation it can be seen from this slide. I just keep going because we have time limitation. So next, talking about CO2 sequestration. You can see from the left side of the schematic how the traditional or conventional CO2 plume migrate quickly to the upward of the structure due to the high or buoyancy dominant. As we know that CO2 has a lower density compared to the resident brine. So later on, we found this as a problematic in terms of efficiency for the storage. The presence of supercritical CO2 accumulated under the cap rock can generate other issues such as CO2 escape toward the cap rock from the fracture, can be also from the corroded cement and sort of things. So that is one of the main issue now for the conventional injection of CO2. You can see also from the bottom right of the plot where all of each of trapping mechanisms in order from the injection to the post-injection scheme, starting with the structural trapping and then residual solubility and mineralization. You see from the the y-axis indicating the security level of each trapping mechanisms. Basically, the basic reason we store CO2 safely to get the higher security for the CO2 storage. So we basically want to store CO2 in terms of solubility trapping in the dissolved brine and also mineral trapping, the safest one. Let's see what is the main problem of the presence of supercritical CO2 within the formation. One of the issues from the Sleipner project, you could see here, due to the quick movement of the CO2 upward, the CO2 plume even passed interlayer shell and reaching the top, the main cap rock quickly from the initial prediction from the operator. And we can also, the lateral distribution of the plume is insufficient, meaning that we have less interaction between the CO2 and brine, less solubility trapping, less mineralization, and less secure CO2 to be stored. Next one is Gorgon project. You can see from that figure, the amount of injected CO2 in that targeted formation requires the extraction of resident brine. It's almost 90% of the volume of CO2 in the expected pressure and temperature. So there is a storage capacity issue, and that might be used for a reason to pass their other project for oil and gas. Energy intensive, and later on they found a same problem in the injector to dispose the extracted water. So some investigator tried to find out how to deal with this. A new technique has been developed, not new, water alternating gas injection is very well known in oil and gas sector. So basically the chase water injected after the CO2 try to control the movement of CO2, fix the mobility, can also increase or enhance the interaction between CO2 and brine, again, more solubility, and later on mineralization, and also natural imbibition. Another conservative technique, carbonated water injection. This technique does not allow the presence of supercritical CO2, but it requires a large storage site, especially for the aquifer. Because, as we know, in the deep saline aquifer, we may expect only 4 weight % of CO2 can be dissolved, which is very small. So it's conservative, but may not be able to store large amount of CO2. And one of promising technique now is microbubble injection. You can see from the right side of the picture of the schematic of the bottom hole assembly to generate the microbubble. There's a specific tools installed at the end of the bottom hole assembly for the microbubble generator. So let's talk about this technique a little bit further. This technique was proposed by Koide and Su in 2009 for a geosequestration purpose. The advantages actually from this microbubble phase are larger surface area and thus enhancing the dissolution process, less buoyancy, so the quick movement to the top of formation can be suppressed, so we can expect more lateral movement for the CO2 for the plume. Sorry. And high internal pressure combined with large surface area can also enhance this dissolution rate. Let's see from the bottom heat map at the middle panel. That is the heat map of the gas saturation. Oh, sorry, let's talk about the bottom right corner first, the Berea sandstone, which is very well known for in oil and gas industry. The top side represent microbubble injection, and the lower one is the conventional one. This heat map, the more yellowish, the more CO2 can occupy the pore space. But here we can see microbubble can penetrate the lower side of the core, while for the conventional one, it just flow through the top of the core. And move to the middle panel, Sarukawa sandstone. It is a tight core from Japan. The same behavior can also be observed. You can see from the black box from the heat map, more reddish color for the microbubble case, meaning that more CO2 occupy the pore space. So we deal with the pore occupancy and try to understand how this pore occupancy can be analyzed. Okay. We use the traditional way, the concept of bundle of capillary tube. Start from the left picture, the simplest one, homogeneous size of the tube. I'm here saying bundle of capillary tube to represent the porous media, rock. So this simplest one, the homogeneous size of capillary tube, you could see the capillary pressure curve depicted by the red arrows as a function of water saturation. Once the threshold pressure is overcome, the wall volume is occupied. But in fact, we deal with a wide range of pore size in the porous medium. So we have a wide range of capillary tube size now. See the next picture. And we deal with that typical capillary pressure curve as a function of water saturation, and the lowest PC, or the threshold pressure, actually represent the largest tube. The less restriction for the infilling fluid to penetrate the porous medium. So let's use the Young-Laplace equation to translate this. It's normally used you can see it from the right picture, two immiscible fluid within the capillary tube, generating a kind of meniscus. So now capillary pressure is a function of the contact angle, IFT, and also pore radius, or tube radius in this case. And as we know, we arrange the equation, now we can relate the pore radius or the tube radius as a function of water saturation, meaning that every single incremental of capillary pressure is represented by any new development of the fluid to the smaller pores, because pore radius and capillary pressure is in the inverse relationship. So the highest the PC, near the irreducible water saturation, basically depicted by the very tiny pore radius. Okay, we're going to use this concept to find out how this microbubble can be simulated. So we start with the one dimension, the simplest one dimension pore flooding simulation. The data was taken from those three references. Basically, they used the same core flooding data, and then they just analyze in the different point of view. The heat map represents the distribution of porosity. We could see some layering there, but by averaging in the vertical direction, the porosity properties is homogeneous. You can see from the bottom left corner picture. And I just took the first two gas saturation profile just right before the gas breakthrough to match the gas saturation profile, just to see the more occupancy of the microbubble and also the late front movement for the microbubble case. They compare microbubble and conventional at the same core, so which is good to be compared. All right, so the one dimension core flooding modeling, okay, should be patient to wait for this. All right, so the simple model, I'm using CMG simulator here with Brock's and Corey relative MPC model. Apologize for that, Mr. Ahmadi, because it's Brock's Corey. Later on, I will use your generative model. So use the typical relative permeability for both cases because none of injectivity issue reported until now, and focus on the capillary pressure because it will translate the pore occupancy later on. You see the red color there regarding the entry capillary pressure. That will be the adjusting parameter in this simple work. Let's see the result on the right top corner. Left figure is conventional injection denoted by CI and microbubble injection on the right. And yes, you see unmatched, especially near the inlet, injection inlet. This gas saturation spike cannot be matched with homogeneous assumption because I use a homogeneous assumption here. And some other investigator observed the same and they relate this as an incomplete water saturation process before implementing the core flooding CO2 injection later on. So the X-ray CT scan read this as a high gas saturation. In other words, near the inlet, the water saturation is not 100%. All right, so I just keep going, and with microbubble injection, the saturation profile can be decently matched. And further, assessing the grid sensitivity, I tried to do a refinement to the grid and ending with entry pressure for the conventional case of 6 kilopascal and for the microbubble one, 3 kilopascal. Consistently, we can see that the entry pressure for the microbubble case is lower compared to the conventional one. And you can see from the top right corner figure, the resulting capillary pressure from the history matching. Assuming the same fluid PVT between those cases, the PC are different. Like there is a shifting of capillary pressure generated by the microbubble case. Later on, we may relate this as a wettability alteration, but let's see the next slide. We recall back the Young-Laplace equation. I cross the pore radius parameter there, meaning there might be the main reason of deviation of capillary pressure may not be attributed to the pore radius because they implement the injection into the same core sample. And I also cross the IFT because we deal with the same fluid system. There is no any chemical mixing during the experiment. So let's see the lower schematic. The top one is continuous CO2 phase and the lower one is microbubble case. In this continuous CO2 phase, the CO2 touch the wall, generating a certain contact angle. You can see the meniscus there. But in microbubble case, there might be some condition that the bubble size is much smaller or smaller than the pore size. And then there is no any capillary resistance for the microbubble to access the pore. So then the microbubble can access the small pore without any resistance, and that might be inaccessible to the conventional one. Let's see the middle panel. It depicts the mass transfer for the CO2 as a function of bubble radius. We could see the smaller the radius of the bubble, the mass transfer rate is also increases. So we know that there is an increase, the enhanced dissolution process with microbubble technique, and probably in the initial state of injection, all of the microbubble just disappear, but like as time lapse, the microbubble just get shrunk. The microbubble getting smaller and again access the small pore spaces without any capillary restriction or zero capillary pressure. And move to the right panel. Credit to our moderator, that's taken from one of his publications, Mr. Miftah. observing the impact of water pH, the drop of water pH to the zeta potential. We could see here that the drop of water pH, in other words, the brine getting more acidic, decreases also the zeta potential in absolute basis. It's in the minus scale. So later on, this drop of zeta potential is related to the less water wet state. So this state gives generates like a more welcoming situation from the rock to the non-wetting phase, which is CO2. So those three mechanisms may be attributed to the shifting of the capillary pressure. But currently, at the moment, we have no specific identification to which, to how big the portion of each reason to the shifting. That will be a future work for my research team, and this is the preliminary one to identify the microbubble capillary behavior. So those are the conclusions. It's simple actually. We can try to match it and identify there is a shifting in capillary pressure and try to find out what would be the responsible mechanisms to the shifting. Thank you so much.
Thank you very much for the presentations. Please move to the seat next to me. We now open the floor for the Q&A sessions. Any questions from the participants? Please raise your hands. Any questions? So if not, I do have one, to be honest. For me, what's the impact of the microbubble injection? What I understand is shifting the capillary pressures versus saturation. What's the impact then for the field scales implementations?
Thank you, Mr. Miftah. This shifting actually give more space for CO2 to occupy the pore space, and then the capacity of the CO2 storage is enhanced. Well, we really need that, and that's the one we investigate here. But another thing is the enhancement in terms of sweep efficiency. Due to the less or very low buoyancy, it's very tiny in terms of volume. Buoyancy is a function of volume. We can expect more a wider lateral movement to the plume of CO2 in the microbubble discrete phase. And then again, enhance the the interaction probability between CO2 and brine, and also enhance the solubility trapping, which is the safest one that we want to reach out. And following this reaction, there is a mineralization, the one that we expect to permanently store the CO2. And yes, this microbubble is promising in terms of enhancing the storage efficiency compared to the conventional CO2 case.
Okay, thank you. Mr. Egi, any more questions? If not, we will conclude the sessions. Thank you very much for the presentations. I do hope you can join us next year to present more results and give us more insights regarding this research. And please give a round of applause to Mr. Egi. Moving on to the next presentations and our last presentations in these sessions today. For the petroleum engineering sessions, the title of the presentation is the comparative study of water alternating gas CO2 injections, performance in a dead oil reservoir using the Blackwell model with MRST and CMG simulator. Please welcome to the stage for the presenters. The time for the presentation is 12 to 15 minutes maximum, and followed by a question and answers. Please. Please wait a bit. Apologies for the technical things. Miss Sahar Banun, yeah.
Yeah.
Okay, apologies for this technical. I would like to invite you for seats next to me. You have to wait about these presentations. Now, let the committee fix these things first. Okay, then the screen is fine, so there is a glitch a little bit. So I hope the participants get, what do you call it, nice relax a bit before we continue the presentations. Okay, then I would like to invite the presenter against to the stage to present uh, her result about the comparative study of WAG and CO2 injections.
Okay.
Okay. Thank you. Please, the floor is yours.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. My name is Syara Bunun from Universitas Pertamina as the first author, and I will present a research study titled Comparative Study of Reage CO2 Injection Performance in a Dead Oil Reservoir using the Black Oil Model with MRST and CMG simulators. Right now, the industry faces many mature fields, thus needs to improve the recovery by conducting EUR. Water alternating gas CO2 is a promising EOR technique for its dual benefits to enhance oil recovery while reducing global emission. Numerical simulation is a crucial tool in capturing complex fluid flow behavior like EOR. While most of the commercial simulator works as black box, this study will compare using a commercial simulator, which is CMG, with an open source one, which is MRST. Okay, the objective of this study are, the first one is to model and evaluate water alternating gas CO2 injection between two simulators. Second, we'll conduct several recovery scenarios and compare them. Then we'll evaluate advantages and limitations of MRST and CMG. And this study has a limitation, which are it employs black oil. Thus, the miscibility will be represented through the pseudo-miscibility atau long stop. And it's a synthetic model. The analysis focuses only on 4 main scenarios, which is water injection, CO2 injection, and water alternating gas CO2 injection. And the analysis focuses only on performance indicators. Okay, EOR, or enhanced oil recovery, refers to a technique that involves injecting a material usually not naturally present in reservoir, aimed to reduce the oil residual saturation. EOR often considered as tertiary recovery, but can be applied early to improve oil recovery. Water alternating gas CO2 is one of the EOR techniques that can improve macroscopic sweeping efficiency by alternating water and gas injection. And the desired sweeping is shown on the screen on the right side. Okay, going on to the methodology, the research workflow will start with the literature review and data collection, then collect and develop PVT data, input reservoir static and dynamic data, then the model will build with 2 simulators and will be initialized. The initialization will be repeated until it has a mismatch under 2% between the 2 simulator, MRST and CMG. Then followed by running stability check, and if it's stable, then we'll continue to simulate model into desired recovery scenarios. Then we'll extract the simulation results and compare them to continue analyze them. Okay, for MRC workflow, it will start with loading the proper modules, then set up reservoir geometry, set up petrophysical properties, set up fluid properties for solvent and reservoir, and then define initial state. Okay, and then we'll continue set up wells for producer and injector, and then we'll set up schedule simulation, then simulate the schedule using linear solver, and the last one is to visualize and plot simulation results. Okay, and for CMG workflow, it implies the same as MRST, but the difference is only the CMG will use CMG IMAX and results feature. Okay, so for the model itself, it will employ a Cartesian grid system with dimension of 7.7.3. Okay, and the horizontal dimensions will span 500 times 500 feet, while the vertical thickness varies across layers. There are 3 layers. And the reservoir initially filled with oil saturation, 80%, and water saturation, 20%, and there is no free gas. And as you can see, for the reservoir properties for each layer, the reservoir has a homogeneous porosity of 30%, and the permeability is anisotropic. Okay, so for the simulation scenarios, for the methodology, for the PVT data, the reservoir is initially saturated, which the reservoir pressure and the bubble point pressure is same at 600 psi. Initial reservoir temperature is at 100 degree Fahrenheit, and the initial oil density is 44.98 pounds per feet cubic, and the reservoir assumed to be dead oil, which is the resolution. Well, GOR is 0 and the BO is 1. The solvent PVT data will took from NIST, an open source chemistry webbook. Also, the mixing parameter will be assumed to be 1, which means it will be completely miscible. So the initialization result shows that there's only a mismatch under 2% between the 2 simulator relatively to MRST. Okay, for the simulation scenarios, the model will have a 1 producer and 1 injector in the opposite corner diagonally. And for the water injector, it will be perforated in layer 2 to Thor at the bottom side. And for the gas injection, it will be at the upper side, layer 1 and 2. And the simulation will be carried out for 20 years of production, as you can see in the left side, at the right side, for the scenarios, where the total pore volume injected is 0.08. The constraints used for producer will be bottom hole pressure only with a minimum of 1,100 psi, and for water injector will be set at rate of 705 barrels per day, and for CO2 injector will be set at rate of 500 millimeter scuff per day, scuff per day. Okay, so for the results, even though the simulation is run with the same laptop and time step, overall CMG runs faster than MRST for all scenarios. And also, at the initial equilibrium conditions, it's by testing, shutting in all wells, it shows that both simulators are stable, that it's ready to simulate under several scenarios for the research. Okay, for the first one is CO2 pseudo-miscibility behavior. Okay, for CO2 pseudo-miscibility behavior, looking at the first layer from case 3, 4, and 5, that includes injecting CO2 only cases. By looking at oil density in pounds per feet cubic, it shows that the oil density is reduced in the injector zone, affected by pseudo-miscibility between oil and CO2. And then its effects will be gradually decreasing, reaching the producer zone. Overall, the performance is same between the two simulators, but MRST tends to predict stronger pseudo-miscibility effects, particularly under longer CO2 exposure. Okay, the next one is for the recovery behavior. Looking at case 2, 3, and 4, with MRST represented through the blue dot and CMG represented through the green line, it's shown that case 2 for water injection has most identical performance between the two simulators. And conversely, in case 3, CO2 injection, it can be seen that the pressure is slightly different, and if we focus at the cumulative oil production that I pointed with the red circle, it's clearly shown that there is a noticeable differences between them. The yield increases most likely occurred due to miscibility effect in MRST, so it will produce more oil than CMG. This also happened in case 4, but its effect is more small because the gas injection is alternated with water. Okay, in summary for the recovery behavior, it can see that the overall production performance tends to remain comparable between the two simulators relatively to CMG, and the water injection exhibit nearly identical recovery performance, and the scenarios involving CO2 injection results in more noticeable discrepancies, especially in a longer CO2 exposure. The next result is in sweeping behavior. For sweeping behavior, in case 2, in case 2 water injection, looking at water saturation between MRST and CMG, it is shown that both simulators have the same pattern and magnitude, only that MRST sweeping tends to be farther from injector from the CMG compared to its CMG. And for the sweeping behavior in case 3, CO2 injection, looking at solvent saturation between MRST and CMG, it is shown that both simulator tends to have the same pattern, only that MRST sweeping has more magnitude and the gas is most likely reach the further distance than CMG. And looking at the pattern, MRST tend to have a pattern with a shape like diamond, while CMG more like a triangle shape. Okay, and for in case number 4, water alternating gas CO2 injection. Okay. Looking at remaining oil saturation between MRST and CMG, it is shown that both simulators have a near same pattern and magnitude, but MRST tends to be more dispersed than CMG. Also, the sweeping is improved than the water injection and continuous CO2 injection scenarios. Okay, so in conclusion, with OIP and oil original water in place mismatch under 2%, MRST tends to overpredict CMG in its performance. And the second conclusion is CO2 injection in MRST have higher oil production, and the sweeping is more fast than CMG. It is because of the greater miscibility effect. And the last one is MRST offers flexibility and transparency, but it also needs deep understanding to use MRST. While CMG is more robust and practical, user-friendly, but it operates as black box, so we can't know the operates inside it. And suggestion for this study, for future study, it is essential to be familiar with MRST and have strong understanding. So you can have to, you will have to deal with convergence issues. And also for the second suggestion is if you want to use MRST, start with simplified model. But for complex model, you can use Eclipse data deck. And for the third suggestion is if anyone want to have a further research, you can have a research focusing on key operational parameter for water alternating gas CO2 sensitivity. And the last one, for future studies, it's most likely to use compositional model to be more accurate. That's all from me, and thank you.
Thank you very much for the presentations. We now moving on to the Q&A sessions. Please have a seat. Any question from participants? Yes, please.
Okay, thank you very much, Mrs. Banun, for this presentation today. We know that MRST is a new thing that in simulator commercial. We know that CMG and TNF and maybe a petrol. And for the based on your presentation today, we know that MRST, if we have to good understanding in coding skill or maybe in good understanding in every single module and function that availability and MRST. Talking about scalability, what is your recommendation or the conclusion between MRST as an open source simulator, between CMG as a simulator commercial? If we talking about the scalability, if we want to use in field scalability. Thank you.
Okay, thank you for the question. Okay, so you asked about the scalability differences between MRST and CMG, the commercial one. So based on my research study, I believe that MRST is more likely to be used on research development, not for practical use, because it is more complex and also it's something that new for everyone. And because we have to understand, like you said, the modules, the function of its code, and etc. So it is more complex. And also, while doing the research study, I've noticed that I think it's for now, I don't know if there's another upgrade for the software. I believe it's more suitable for a small scale, like laboratory scale, or focusing on something smaller, not for a field large scale like CMG that is robust and also practice and it's user friendly. So especially if it's including decision making. So I believe for using CMG, it will be more practical commercial simulator than MRST because it is more likely for research focused studies. Does it answer? Okay.
Thank you very much. Any more questions? If not, so we now conclude the sessions. Thank you for the Ms. Banu for the presentations, and thank you for all the participants. I would like to invite the other presenters first to the stage. Miss, I'm not sure who has been present here, still in here, possibly Mr. Egi, and other presenters who are still in this auditorium to receive a certificate from the chairman. Please have, I would like to invite the chairman to give the certificates for the presenters for these two sessions, especially for petroleum engineering programs. Oh yeah, Ms. Fadila, please also. Om dulu. Miss Fadila.
Okay, give applause one more time. Oh, I said it. Please give
Thank you.
applause one more time for the speaker of this session. Thank you very much for Bapak Miftah to lead this session. And ladies and gentlemen, as you are now entering the lunch time, you may enjoy the lunch and take a break and take a rest. But please don't go anywhere because at 1:15 we should start the poster session. And for Muslim who want to take pray, we also have the praying room at the right side. And see you in the poster session. Thank you. Check. Check. Welcome back. Welcome back, ladies and gentlemen, to ICGRE 2025. Now, we will begin the poster session. For this poster session, we invite all of the poster presenter to stand beside their poster to explain the audience about the result of their study. And to the audience, you can stroll around the poster displayed at the back, and do not hesitate to convey your curiosity or anything comes to your mind while reading their paper. The duration of this poster presentation is 30 minutes from now. Kepada para hadirin pada hari ini, apakah ada yang tahu ini punya siapa ya? Ada kunci motor Vespa warna navy, ungu. Barangkali ada yang merasa kehilangan, boleh menghubungi saya ya. Terima kasih. Anjay. Mana ini Pak? Mana yang punya poster yang udah nggak ada? Yang punya poster udah nggak ada. Iya, kayak nggak kondusif gitu deh tiap poster. Poster kan Mas Edi ini, dia tuh moderatornya buat Mas Vera, Mas Reksa. Terus ini yang Mas Dudunya. Iya. Aduh, ntar dulu ya, kagak ntar. Ini mau diarahin lagi nggak? Posternya? Ya. Iya, boleh Mas. Coba. Ya, diarahin lagi ya. Iya. Coba mana sih? Gue tuh kayak kalau ngomong rada-rada. To representative of each paper, please stand beside your own poster because the audience want to know more about your poster. Check. Okay, ladies and gentlemen, as the time for the poster presentation is ended, we would like to invite all the representative of each paper to come forward to grant the certificate of appreciation from the committee. We also invite the committee to come to the stage and give the certificate of appreciation. Ada list nama. List nama poster. Sesi foto kemarin itu karena ininya nggak ada. Oh, nggak poster. Gimana aja ya? Ya. Gimana? Gimana baiknya, Mas? Baiknya gimana, Mas? Okay, for documentations, we would like to grant the certificate at the poster booth. Di mana? At the poster booth, so we will get the better documentation, yeah. To Vera Gushiva, you may come to the booth. To Ibu Vera Gushiva. To Bapak Muhammad Dafa Izar. To Bapak Miftah Afrah. Bapak atau Ibu Miftah Afrah. Selanjutnya, Bapak Riza Rizky Aisyah. Ibu, maaf. The next one is Ibu Niken Inriani Babai. And the next one is Bapak Rudiat Hari Sukma. The next presenter is Bapak Miftah Adi Rohman. Bapak Miftah Adi Rohman. Itu juga skip. And the next one is Bapak Muhammad Imran Azhar Mangkona. And the next one is Ibu Fitria. And the next one is Bapak E.T.A. Farhan. And the next one is Bapak Rio Wansyah Pratama. And the next one is Muhammad Rida Fikri. The next presenter is Bapak Agung Subangun. Bapak Agung Subangun. Tidak ada. And the next one is Ibu atau Bapak Izuki Hamida. Oh ya. The next presenter is Bapak Brema Kris Bantat Ginting. We would like to invite again Bapak Miftah Afrah. Ibu, mohon maaf. Udah semua ya? Okay, thank you very much for all the hard work and contribution from all the poster presenters. Please give applause one more. Ladies and gentlemen, we are now about to begin the third plenary sessions of today's agenda about the geophysics engineering that will be delivered by Bapak Erdin Saigin and will be moderated by Bapak Reksa Verdora. To Bapak Reksa, we invite you to come to the stage.
Assalamualaikum warahmatullahi wabarakatuh. Selamat siang Bapak dan Ibu saya hormati. Good afternoon everyone. So now we are going to start our last plenary session. And this afternoon here with us is present Pak Erding Saigin in Zoom. Pak Erding, can you hear us?
Yes, I can hear you. Can you hear me?
Yep, I can hear you clearly. So it's unfortunate that Pak Erding cannot visit Indonesia, but thank you Pak Erding for taking time for us this afternoon. Thank you for taking time for us. And before we start, I would like to introduce our presenter today. So, Dr. Erding Saigin is a principal research scientist at CS Cairo, where he leads the geophysical sensing and monitoring team, and he develops and applies novel seismic methods to investigate large data sets, advancing understanding of Earth structure and dynamics. His research focuses on computational and observational seismology, with application global energy transition. And this afternoon, Pak Erding will present us a very interesting talk for the imaging of the Australian crust across scales for resource exploration and environmental monitoring. So Pak Erding, you will have 20 minutes for your presentation, and then after it, I think we will allocate around 10 minutes for audio.
Oh, okay. Maybe I will try to connect again. This is complaining. If you give me a minute, I will do that again. Apologies. Yeah.
Okay, so we need to wait for Pak Erding. He still try to reset his computer. So maybe we can wait 5 minutes. Yes, Pak Erding?
I'm sorry, I'm back. I tried to share my screen again. Give me a minute.
Yep. Take your time, it's okay.
Oh, apologies for this. We are not, unfortunately, okay. System seconds. Sorry, I will do my, okay. Okay.
Okay, there is still some technical problem, I guess.
Okay, I'm back. I hope this will work. Okay, now I think I will manage it. Okay. Okay. Can you see my screen?
Yes, we can see your screen. Yep.
How about now?
Yep.
Okay, perfect. My sincere apologies for the delay. As I said, we at CSIRO, we are normally Microsoft Teams people, so for that reason, some of the permissions were not set. Thank you very much, Pak Reksa, for introducing me, and I would like to thank all the conveners for inviting me for this great opportunity. My sincere apologies for not being able to make it today. I wish I was there, but I will do my best to deliver this talk. Hopefully, it will be an interesting and interesting session. Quickly, so my name is Erdin Saygın. As Dr. Reksa introduced me, I'm the principal research scientist, also team leader at CSIRO, which is the Australia's National Science Agency. And today I will be talking about the 4D imaging of Australian crusts across scales for resource exploration and environmental monitoring. A number of people have been involved, so I'm just purely the messenger, but please get back to me if you need a specific question. Okay, so our work, CSIRO is a pretty large place, but our specific work about energy transition is particularly about the decarbonization of the industry and transport, and also research in carbon management technologies. There are several sub teams beneath that, but the critical bit is about how we're looking for ways how to reduce carbon emissions of the industry by studying this electrification and also carbon abatement technologies, but also we looking at the other techniques to how to reduce that CO2 release. So I'm a seismologist, although and I will be mainly focusing on the seismic applications. But before diving deep into what we can do with seismology, I want to bring your attention this future gas strategy, which published a bit over a year ago in Australia by the Australian government. Future gas strategy is freely available at this bottom link. You can go and download. There are several things how Australia should manage this transition, but there's an interesting statement here. If you look at the three which I highlighted, it's under the new source of gas supply which are needed to meet the demand during the economy-wide transition. It specifically says, where possible, minimize the active seismic survey. Now, this may sound a bit interesting, but this is a pretty contentious topic in Australia especially, which actually limits several operators and also acquisition companies to go and do new offshore seismic surveys. Onshore industries also probably will be following the lead, but in general, the landscape is quickly changing, and seismic is not anymore the go-to technology because of these restrictions. So now this is very and I already mentioned that this is becoming increasingly challenging. We need minimally intrusive and cost-effective alternatives, and also maximize the value of our data sets. From now on, I will be talking about some of the outputs that we've been working and the relation to the energy transition. It may be disconnected, it may look like disconnected, but in reality, our eventual goal is how we can explore the subsurface in the best way possible with minimally invasive and cost-effective techniques, and also how we can add value to our data sets. So many of you heard about this ambient seismic noise imaging. I just want to remind you quickly. Now it has been around a bit over 20 years, the form that I will be talking. In a very simplistic sense, we deploy sensor networks on the ground, and then we record the continuous seismic noise, and from that we correlate that. That correlation yields mainly Rayleigh type waves, which is highly sensitive to the subsurface, and from that we do all sorts of inversion to probe the subsurface. One of the key parameters is the dispersion, what we call. I mean, if you don't know seismology, you can think like this. On the right hand side, when a seismic wave starts excited, when it's propagating with different old frequencies, the higher frequencies tend to sample the shallow earth, which is slower, and lower frequencies sample deeper part, and which is in general faster velocities. So at the end of the race, lower frequencies most of the time arrive earlier than higher frequencies. That itself is a very useful information because we know that subsurface is not homogeneous, so we can measure this kind of dispersion of these waves, and from that we can probe the subsurface. Now, passive seismic imaging, there are great examples from Indonesia, and I had the privilege to work with some of the scientists. But I will be talking about a bit different technologies here, that how we add value to our data sets. In this particular case, we look at those sensor networks and try to reduce the dependency of our dependence on the simultaneous recording requirements, where if you want to get that correlated signal, your sensors normally need to work at the same time. By just relaxing that criteria, 5 years ago, we demonstrated that we can actually utilize stations which were not necessarily working at the same time. Now, that's exactly a good example to adding value to the data, and because, I mean, that's how it's as an example from offshore Australia. Back in 2015, a dense array was deployed in northwest shelf of Australia for oil and gas exploration, which was actually a moving array, as you can see on the right hand side. Normally you can only get information from those red patches, but what I will be talking about, this new technique that we developed, you can now start to make these different patches at different time frames talk to each other and get real measurable signals. On the left hand side is how the conventional technique will give us that information, and the right hand side is a new method. But here the key thing is, with this new information, we reorganize the information and we increase the number of measurements. We applied this to Australia. First, in the 5 years ago, the technique that we first had to benchmark it, whether the conventional technique would work versus what we call asynchronous, because the sensors are not working at the same time. The answer was right. I mean, top one is the conventional technique and the bottom one is the asynchronous. But the beauty of this technique, we don't necessarily compare them, we want to combine them, because when you combine the measurements, your resolution will also go up as well. We applied this for different settings in 2020 to show that what we get is not a signal processing artifact, it's a real thing, and show that for also South Australia, for 2 different cratons using waveforms one from 2008, the other from 2013, and we get still meaningful information. But the big thing was, we later applied to the whole continent. Now, Australian continent, the passive seismic sensors, unlike Indonesian one, are quite distributed unevenly, and most of the time temporary deployments are used to cover the continent. So as you can see, there are huge gaps in the coverage, although this will be changing because of some of the new initiatives, but overall we still have a major data gap. Now, why is it important? These figures are showing the conventional technique, the distribution of the density of the measurements versus the asynchronous one. But as I said before, when you combine them, that's where we get the biggest jump. Combined ones, this is just 2 instances. One is 5 seconds versus 20 seconds. Our measurements density went up, and we take these measurements, image the subsurface. From now on, it's the ambient seismic noise tomography with this new data set from all the way to the upper crust to lower crust. It's very exciting, but so what? So what question is very important, and that's why I think I'm showing this example to you. Once we get these velocity slices for different depths, we also look at the distribution of that. And here, these histograms are showing the distribution of those velocities in the continent, for the whole continent, which is the blue, dark blue, the Gaussian curve, versus the locations that we know mineralization is occurring. That's the average shear wave velocity. We look at this systematically for different depths from 0 to 10 to 10 to 20 and so on. What we found, the average shear wave velocities from these synchronous ambient noise tomography are in general higher than the continental average under the zones that we know there is mineralization. So, and that's pretty much covering whole crust, which is exciting. It's not just the upper crust or near surface. This is suggesting us the whole mineralization is happening, the process is involving the whole crust. So this model now is adopted by several exploration companies, because in general Australia is covered by thick sedimentary cover, so it is important. So this gives a good starting point. Now I've been told that I was expecting to have a bit more time, but for the sake of the time I will jump. We just don't work on the also ambient noise tomography. We revisited the good old HVSR technique, and that also gives very useful information, because with again the same team, we want to add more value to the same data sets. With the same data set or passive seismic data set where we can do ambient seismic noise tomography, we can also look at the single station measurements as well. In literature, this is being called HVSR, Rayleigh wave electricity, but the underlying mechanism is the same. We look at these measurements and we try to probe the subsurface structure. Now, the conventional approach, I keep saying conventional here in a sense that where the adopted one, especially in Australian industry, is an empirical formulation where they look at these peaks and they map to some depth profiles. We don't do that. Instead, we directly invert these curves. Now, why is it important? Because once you do that, you get again a velocity profile between the station. Now the scale is very different. Previous slide showed continental scale. Now it's tenement scale. In this image, you can see that we clearly not only map the depth to basement, but also we delineate the stratification in between as well. This is particularly important for explorers in Australia before targeting their drilling. Recap my points. So we use the same data set, one for continental scale and the other for tenement scale, getting insights from the subsurface across different scales. We apply the same thing in the continental scale as well. It's an ongoing work of my colleague Mehdi Kashgai. It's currently been applied to Western Australia, which has both cratonic structure and also thick sedimentary basins. And again, it will be guiding the explorers, mineral explorers. Now, I want to a bit change gears, and hopefully this will make a bit more sense. So, back to this, I want to remind you that the active seismic, especially in offshore domains, is hard. Not only is very expensive, but also with the new future gas strategy, it became harder to go and collect data. Not impossible, but the tendency, the approvals are getting highly scrutinized. So, in this particular work, I briefly mentioned about at the beginning of my talk, we use this 2015 data set from Northwest Shelf, which is literally in this small rectangle, a very dense ocean bottom network, ocean bottom nodal array. This was a 3D active seismic survey. They continuously did shooting 24/7, but in between there was some enough passive seismic energy that we could have used. We did our usual correlations and get this what we call Schulte waves, which look very good. But also we realized that these arriving Schulte waves tend to change very small amounts. Their arrival time tend to change depending on the day of the time, but this is more like a cyclic thing. Now, people have shown that in the past, time-lapse measurements can be done with seismic ambient noise, especially onshore, because of the effect of the rain or atmospheric disturbances. But in this particular case, it's probably the ocean, tide-induced ocean column loading. But that's a part. What we did in this particular work is we take these measurements. This is actually showing another way of looking at the data. It's just showing the velocity decrease at certain times and then recovery. But when I say velocity decrease, I'm talking about like up to 1% in absolute sense. It's very small. Again, the question is, so what? What can we do with this? Now, my colleague Pango from my team designed this a 4D double difference FWI workflow. He took these measurements, those small changes, and inverted them across around an FWI model from the average Green's functions or Schulte waves. On the right-hand side, you're seeing snapshots of the velocity model as a function of that for different time frames, from the 1 hour, which is corresponding to here, or when the velocity is high, or when the velocity is going down, and that's what you see. If you look at the color bar, you will see that the variation is 6 to -6%, this is the shear waves. In short, we are mapping the subsurface with these purely passive seismic signals and in a repetitive sense. Now, I will be coming to this why this is important, because especially for carbon capture and sequestration projects, MMV, monitoring and measurement, monitoring and verification is particularly important, and often 3D active seismic is used repeatedly, which is 4D seismic. It's expensive, and as I said before, in Australia, it will become very hard to do that. So with this alternative technique, we have a path forward, and I will be talking about that. Now, I'm not going to go to DAS because my time is limited. My sincere apologies. I never like doing that, but we are also looking at the DAS datasets and earthquakes. But I will jump to this and jump to the carbon capture and utilization. I think this is particularly important topic for Australia and also Indonesia. In a nutshell, the eventual goal is you want to capture the CO2 which is emitted by factories, large sources, and take that with some proper engineering, put to inside in the subsurface with the right geology. Now, in an ideal world, that CO2 will stay forever, but we know we don't live in an ideal world. So we need to monitor that. Briefly, I mentioned that for offshore and or onshore, 4D seismic is the go-to tool, but it is expensive and it is intrusive. Now, our gas strategy mentioned that seismic is not really where possible avoided, but also there is a social license aspect of it, where several people thinks that the seismic acquisition activities is affecting the marine mammalian communication. Now, whether this is the case, that's beyond me. It's a still contentious topic and requires further research, but this doesn't change the fact that there's a social license aspect of it. So what can we do? We can't simply ignore this CO2 which we injected, because we're hoping that will stay there for a long time, but also we need to monitor it, and if there is something not going in the way that we plan, we need to take action. So active seismic is not good. What we did in this particular work, this is a desktop study because it's extremely hard to find real offshore data with CO2 injection. Either the data is not available or operators do not want to share it, but we were lucky to use a realistic velocity model from Pelican site, Victoria, which is simply here. This is one of the designated sites that will be operational in the coming years. CarbonNet is the name of the project, and it's a reasonably shallow water, and the projected storage is around 5 million tons per annum. So we take this, and in this next slides, I will be showing that what technology is the best way to tackle this MMV problem. Can we simply just go straight passive seismic, or do we need to do active seismic as well? So at this place, they did a 3D seismic survey in 2018. It's a real survey, and we were lucky because we take this as a baseline, and we put hypothetical CO2 bodies in it, and also some migrated CO2 as well. On the middle side, you can see that's in a relative side, so it's easier to see. And our question is, can we image these anomalies if we use conventional seismic reflection with conventional, like a tall streamer type setup, or can we also use conventional seismic sources with an offshore seabed DAS cable, which I will be talking, and also the passive seismic technologies. So for the first example, this is hypothetical. We put 21 sources, which is not too much, and source spacing of 500 meters. You can think this more a towed stream. And in the DAS, it will be different. So the first one is the conventional, just standard, double difference FWI. Right-hand side is the ground truth. Left-hand side is the what we can get from the FWI, which is good because we added some noise and we can still recover these anomalies. But as I said, this is the most expensive option. Can we reduce the cost by using a ship, but a permanent cable? So that's the DAS. Literally, we put a cable on the sea surface in the computational domain, of course, and a ship does some sparse shooting. And again, we carry out this double difference FWI workflow and compare what we can get. That's the inverted baseline, and also this is the inverted time-lapse change. With some smear, except some of the smearing, in general, we can get the general anomaly shape, which is very promising. This is not as expensive as conventional, but still you need to deploy a ship and get all, and still it's an intrusive in a sense. How about passive seismic? So passive seismic is, I briefly mentioned in the previous slides, we will approach passive seismic in two different approaches here. One is the conventional ambient seismic noise, and we will correlate and we try to get those velocity models, and then also we would like to use earthquakes. Now, on the left-hand side, we realize that our previously quite deep anomalies are not good for passive seismic. It's way too deep, and our standard cable, we can't recover it. But what we did, we changed the scenario here a bit. Instead of imaging the baseline CO2 or migrated CO2, we are asking the question, what if there's a leakage? In other words, the CO2 seems to migrate to all the way to the surface. Can we use passive seismic? So here we're showing how we simulated the passive sources. We just put randomly distributed sources, recorded DAS, and do cross correlation, and applied a wave equation type dispersion inversion. If this is the true leakage anomaly, with just using single cable, that's what we can get. And bear in mind, this is a super fast technique because we are just inverting the dispersion curves, not the waveform, although the simulation is full elastic. And you can do this, you don't have to run the DAS all the time. You can turn on, turn off, and get your results. So it's a quite fast way. So it is, overall, it is promising. We can get this leakage. So here, passive gives necessary, it's not the ideal situation because there's a leakage, but you don't have to deploy a ship to get this leakage, the location of this leakage anomaly, and how shallow it became. How about earthquakes and microseismic? Now we know that when you do an injection for CO2, most of the time you induce some microseismic activity, and that's mainly beneath the in the vicinity of the injection point in general. And can we use them? That's one question. That's the microseismic events. And the other scenario is, can we use far field earthquakes? And that's, I think, highly applicable to Indonesian case. Here, rather than using one surface, like sea bottom DAS cable, we use 5. In reality, it's actually doing a looping type cable. And we again ask the same question. If we have a baseline model like this is different sections of it, and a monitoring model, what can we get with these earthquakes? Also, what can we get with the microseismic events? And that's the location of these microseismic realistic events and earthquakes. Now, unlike the other flavor of passive seismic, both earthquakes and microseismic events have one difficulty, and that is, if you want to monitor if you want to image the monitor one, you cannot, you do not have any control there on their occurrence time. So in other words, they can happen in between of these snapshots. So we also look at that. This is another way of looking at, and if you our aim is to recover these with 2 different classes of data sets. So with 10 earthquakes, we added noise with the full earthquake FWI. We can still recover with different levels of amplitude the general shape of these baseline anomaly and also the inverted time-lapse change. The great thing about that, we did not use a single ship. It's just a permanently deployed cable. Again, you need a bit longer recording periods, but look, hard drives are cheap, so compared to the deploying a ship and also getting the permissions. What about the microseismic? Now, microseismic gives a better result as expectedly because the energy is literally coming beneath the reservoir and illuminating the surface subsurface, and we get that response in the dust cables. So if you, I mean, I think the image is talking to itself. With some smearing, it gives quite good results. Again, these are desktop studies, but we added we did add noise and to simulate a realistic environment. Now I'm about to, I think I'm pretty much come to the point of my end of my talk, but I want to summarize what we can do. Seismic data is a really rich source of information, but applying the correct physics is the key thing. And also we need to understand the sensor limitations. Environmental change, there are tremendous opportunities in there. We know that we can measure that. We can either take those changes to further calibrate our measurements, depending on the purpose we are after, or use those changes to image the subsurface. Now, I'm repeating myself, active source seismic, particularly for offshore, is becoming more challenging. We can't collect this data. Passive seismic, actually, that was, now I give a different spin, but also we need to understand we need to have a realistic expectations about the limitations of the passive seismic, about its resolution capabilities. It is not the solution. It's not a one-on-one replacement of active seismic, but it can fill big gaps. Other geophysical techniques, depending on the context, like airborne EM, MT, gravity, will be key, I think, to get a quantitative approach and also particularly get an estimate of the uncertainty. On that note, I'd like to thank you for your attention. I'm happy to take any questions.
Yeah, thank you, Paring. It's a very interesting talk, I believe. So I would like to give the time for the audiences. Is there any questions? If okay, I think while we're waiting a question from the audiences, Paring, I think I've been wondering about a thing that, yeah, you also mentioned it in your summary about the expectation, about the resolution and stuff. And we can see that one of the application of this seismology using passive seismic.
Yes.
And you show a lot of application in Australia, and I believe that we can do same thing also in Indonesia. And my question is, from your study cases, what lessons that have you learned about applied these approaches? And my basic question is how we start. Perhaps you have some comment about it.
Okay, thank you very much for the good question. First of all, as I said at the beginning, I had the privilege to work with many of you several years ago along similar topics. First of all, I think Indonesia is in a better situation because in a continental or a large-scale sense, you have more data than Indonesia and much more regular, thanks to the BMKG's continuous efforts, but also university sector. I think they've been collecting really good data sets. I think the first point is there's so much information to be explored and to use. So probably the first step will be how to homogenize the data and how to facilitate the data access. The second one is, now I didn't have a chance to talk about it much, in my talk. DAS is, Indonesia is a large country, several islands, and you have, for that, you need to connect them to each other, right? Probably using offshore cables for that purpose. There's an opportunity to use this distributed acoustic sensing or fiber sensing to get more data from the places that we weren't able to do it in the past. So that's the other, I think, opportunity. Other than that, I think Indonesia is quite advanced. I'm following from the far, like yourself and the members of ITB and other universities. I think seismology is quite advanced in Indonesia. Yeah, so does that answer your question, Pak Reksa?
Yep, thank you, Pak Ading. We still have a time for one more question, please. Is there any question from audiences? So, so I believe all of the presentation is understandable. Is there any question or perhaps something you want to discuss? Perhaps from students there? Is there any question? Okay, yes, please.
Thank you, sir. This is a very interesting presentation. And since I'm from geology, so this is something new for me, actually. I'm Alin, sir. I'm from ITB. I'm from Geological Department, Go Geology. I'm the only one here, anyway. What I want to ask is, in terms of errors and challenges in applying these methods, what are the biggest errors and what do you do to reduce it? And I was curious, in terms of geology, how detailed can the seismic things be applied? And do you need I don't know, maybe confirmation in the field from the rocks maybe? That's all, thank you.
Thank you very much. That's actually a pretty good question. I really appreciate it. The first of all, errors. We always have errors in our measurements. Errors come from the measurements, errors come from the choice of the physics that we apply, and also the inversion or the modeling aspect of it. So how do you mitigate that? First of all, you need to be aware of what you are dealing with. The second one is more and more we use probabilistic techniques, which gives a quantifiable uncertainty about our images, in other words. So those images I showed briefly in my talk, those colorful images, they all have uncertainties. So probabilistic techniques are very good on at least giving some hints about what you see may not be trustable. The second question is, what else can we bring? So absolutely, the geological information is very important, and often, especially for tenement scale, we work with our colleagues from geologist colleagues if they have, and the first thing is they obviously have an expectation in their mind. We need to understand that. So we can't simply just blindly go and invert the data and present that results. So it's very important to keep that communication open and have a clear mindset. The other is, yes, surface measurements are very important, but also one has to be careful that some of those surface features do not necessarily go to the deep. So that needs to be agreed. The third one, I think if you have drilling information, in situ drilling information with some well logs, that's I think that's the key thing that we can easily, and that's what we do actually right now. We adapt to our inversion, the modeling framework, to reduce the search space and also reduce the uncertainty.
Is that answering your question? Yep. Thank you, Pak Ring. So we come to the end of our session. So thank you, Pak Ring, and thank you for all of the questions. And so here, Pak Ring have shown us that a lot of opportunity can be open using application of passive seismic. It is one of the application of seismology, and it can be very beneficial if we can conduct it especially in our cases in Indonesia. It open a broad opportunity, I believe, and also there's also taking a keynote from one of question. Then of course we need a lot of geological information to also validate our result. So thank you, Pak Erding.
Thank you,
Please
my pleasure.
give an applause for Pak Erding. So I would like to invite the chairman. So Pak Erding, we will take a picture first. May you please open your camera? Yep. So
Yeah.
we will take a picture. So actually from the committee we have a memento for you, so we will keep the memento. Perhaps that we can bring it to Perth.
I hope so.
Perhaps later. Thank you, Pak Erding.
Thank you. My pleasure.
Thank you for such an impressive explanation from Bapak Edring and to Bapak Reksa to run these sessions, and we're about to continue to the next third technical sessions discussing the geophysics engineering, and will be moderated by Ibu Dona Sita Ambarsari. To Ibu Dona, please come to the stage.
Okay, good afternoon, ladies and gentlemen. Thank you for joining us in technical oral presentation for geophysical engineering. And introduce, I am Dona. I am lecturer at Geophysics Engineering ITB, and I will be your moderator for this session. Okay, in this session we will be discuss several topics in geophysics, including global geophysics, hazard mitigation, and exploration and engineering seismology. For this session, there will be 5 presenters in this session. Each presenter will be presenting the material in 10 minutes, and then following after presentation, we will open the Q&A session, maybe around 5 minutes. So, starting at 2:40, so each presenter will be presenting the material in 10 minutes. Then the Q&A session will be around 5 minutes. Okay, the first presenter will be presented by Marianto. Mr. Marianto, with the presentation title is Preliminary Result of the Petromagnetic Study of Lavas from Lamongan Volcanic Field, Indonesia, a case study in Kenek Cinder Cone. So for Mr. Marianto, please, the time is yours.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. In the first time, I would like to thank to the committee and the moderator for giving me opportunity to present our preliminary research. And the title is Preliminary Result of Petromagnetic Study of Lava from Lamongan Volcanic Fields, Indonesia. My name is Marianto. I am a student of Department Geophysical Engineering under supervision of Professor Satria Bijaksana, Professor Mirzam, and Professor Andri Dianugraha. Okay, in the introduction, our study area is in the Lamongan Volcanic Fields in Lumajang Regency, East Java Province. You can see in the left picture, Lamongan Volcanic Field is monogenetic field that consists of 61 cinder or spatter cones, marlex, and 3 volcanic fan. And the Lamongan volcano is the main volcano at the center. Okay, in the center of the volcanic field, you can see the lava flow. Based on the previous studies that have been conducted, there has been no petromagnetic study to examine the cyclicity patterns of lava flow that occur in principal polygenetic volcano in a monogenetic volcanic field. So, in the Lamongan volcanic field, you can see there are many manifestations like cinder cone by black dot. So by the black dot and marlex and lava flow. The objective of this study is to determine the characteristic and to identify cyclicity pattern of historic lava eruption of Lamongan volcano. So, in this preliminary result, we focus on lava eruption of Lamongan volcano. Okay, this is the method. The flowchart of our research is lava sample collection. We collected 8 lava sample eruption from 8 different years. From years 1821 until 1898. So there are 8 different flow eruption. After we collected the sample, then we doing the preparation sample in the laboratory, and then collecting the data by laboratory measurement, processing the data, and doing the data interpretation. This is the measurement for collecting the data. There are 6 measurements. The first one is magnetic susceptibility using Bartington MS2B susceptibility meter. And the second one is IRM, isothermal remanent magnetization. And the third one is magnetic hysteresis and thermomagnetic. The 3 measurements we do in the laboratory in India, in National Geophysical Research Institute of India. And then the 5th measurement is petrography, and the last one is geochemistry by X-ray fluorescence. Okay, we continue to the result. In this table, you can see in the result of magnetic susceptibility measurement. There are 8 samples representing the 8 different flow eruption. The mass specific magnetic susceptibility vary from from 1000 until 2000. With overall average of 1,600. And the frequency dependent magnetic susceptibility vary from 1.35% to 2.71%. By the magnetic measurement, I can highlight low CFD indicate that the superparamagnetic grain contained in the sample are slightly less than 10%. Okay, we go to the next result of isothermal remanent magnetization. This is the 8 measurement result of the IRM. By observing the graphic, we can see remnant magnetization begin to saturate at a magnetic field of around 3000 oersted, indicating that the lava sample content is dominated by the magnetite materials. And for the result of the thermomagnetic, the curve between magnetization against temperature, and in the left bottom side, this is the table of list of temperature Curie. The Curie temperature is in the range 577 until 571 Celsius degree, indicating that the magnetic mineral content is a magnetic mineral in the titanomagnetite series. And for hysteresis measurement, hysteresis loop show a pattern of a narrow space in the middle of the curve, indicating that the rock sample is dominated by pseudo single domain. And this is the result of geochemistry X-ray fluorescence for the major element in percent. From the result, I can highlight calcium oxide content tend to increase from 1821 lava eruption to 1898 lava, indicating there is a calcium enrichment. And this is the total alkali silica diagram, and gallium oxide versus silicon oxide. By the diagram, the historic lava of Lamongan volcano can be categorized into moderate alkaline magma series and the basaltic, trachy, andesite rock group. And this is the petrography analysis of lava Lamongan volcano. Identified mineral plagioclase, pyroxene, and opaque mineral. And especially for plagioclase, we can indicating the calcium enrichment, and this is supported by the XRF result. There are increasing in calcium oxide, and I can interpret that the interaction of magma with carbonate rock from the Leprak formation, the northern part of Lamongan volcanic field. And for the discussion, I try to analyze the variation of petromagnetic parameter against the eruption time, from the older eruption to the younger eruption from 1821 until 1898. There are some petromagnetic parameter, from magnetic susceptibility on the top until hysteresis parameter. From the graphic, I can highlight the variation in the Curie temperature, which relatively increase and decrease, indicate a cyclicity pattern of eruption of the Lamongan volcano. And this is the proposed eruption cyclicity model. What happened under the surface in the magma plumbing system in eruption time of 1821. We can see the magnetic parameter of magnetic susceptibility, CLF, and temperature Curie relatively increase. Okay, and the petromagnetic property of lava vary due to the fluctuation in the magma erosion rate and the temperature pressure condition inside the magma plumbing system relative to the eruption timeline. And then the continue to the eruption year of 1847, which the magnetic susceptibility and temperature Curie, both of them relatively decrease. Decrease described by the short row. Increase represent by long row. For the red color and green color represent the relative increase or decrease of magma temperature pressure. From eruption year of 1821 until 1877, both of magnetic susceptibility and temperature Curie is relatively increasing and decreasing together. But start from the eruption year of 1883, you can see the magnetic susceptibility increase, but the temperature Curie is decreased. In eruption year of 1885, oppositely, magnetic susceptibility is decreased, temperature Curie is increased. And finally in 1898, there is inconsistency between relative change in magnetic susceptibility and Curie temperature in the last 3 eruption. And I interpret this indicate that the lava eruption cycle began to be changed and finally ceased to occur after 1891 eruption. Okay, and the final one, based on the analysis and discussion, we can conclude the magnetic mineral of lava are dominated by the pseudo-single domain of magnetic and magnetic mineral in the titanomagnetite series with a low mixture of superparamagnetic grain. And then fluctuation in Curie temperature pattern exhibiting alternating increase and decrease suggests a cyclic nature of lava eruption in the Lamongan volcano. Petromagnetic properties of lava vary due to the fluctuation of magma eruption rate and temperature pressure condition. Okay, I think that's all. Thank you for your attention.
Okay, thank you for the presentation from Mr. Marianto. Is there any question for Mr. Marianto from the participant or student? Okay. If there is no question, I would like to ask one question. I don't know, I have my my expertise is not in magmatic, but I would like to know about, is there any alteration process in this Lamongan volcanic mountain? Is there any recrystallized mineral in this Lamongan volcanic mountain? Okay.
Okay, thank you for the question. Based on the petrography analysis, yeah, we can identify the microtexture of plagioclase. This microtexture indicating there are some magmatic process in the magma plumbing system, I think, yeah. So in the petrographic microphotograph, yeah, I can identify fine sieve and coarse sieve, and the microtexture related to the for fine sieve is related to the calcium enrichment, and for other microtexture represent the other magmatic process, maybe like crystallization, alteration, etc. Yeah. Fine sieve and coarse sieve is two of the other microtexture, Miss Donna. There are some other microtexture, yeah, maybe like glomerulus, etc. Yeah. For the crystallization, I don't identify in my research, yeah. But this is a good suggestion, yeah, and for the next analysis. Okay, thank you.
Okay, thank you, Mr. Marianto, and please give applause to Mr. Marianto for the presentation. Okay, thank you, Mr. Marianto, and we move to the next presenter. The second presenter is from Mr. Iqbal Ramadan, with the presentation title is Directional Characteristic of Ambient Noise Source from Low Wave, a case study of Penajam Pasir Utara and surrounding regions. Okay, please Mr. Iqbal for presentation. The time is yours.
Oke, baik. Bismillah. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. I'm Iqbal Ramadan. I will present in my research about directional characteristic of ambient noise source from low wave, a case study of Penajam Pasir Utara and surrounding regions. To provide a clear foundation about my research, I will present about ambient noise tomography, characteristic of ambient noise source, and the reason for selecting Penajam Pasir Utara for focus area. Let's begin. Surface wave tomography based on ambient noise has evolved in improved approach for exploration geophysics for characteristic subsurface structure and understanding spatial distribution of seismic noise. The technique utilized by seismic interferometry, where wave propagation between station pair is extracted with cross-correlation in long-term period. Ambient noise tomography possesses key advantage because it doesn't depends on earthquake distribution. So, ambient noise tomography work by utilizing ambient noise source for a long time, and it's come from random noise. Where we can cross correlation, we can retrieve empirical green function. The empirical green function contain about travel time delay between station pair. And for this delay, we can estimate about wave propagation. The velocity information, we can extract to information about tomography for imaging subsurface structure. Noise source originally utilized by microseism generated by ocean wave interaction. Can create about surface wave. From surface wave, I'm trying to extract about relay and log wave. For the analysis, I take about log wave from tangential component because it's contain about important complementary information about polarized subsurface. The azimuth analysis from causal and acausal of cross correlation become important to identify about dominant direction for noise source. For amplitude or asymmetry and symmetry can to found about heterogeneity or homogeneity direction wave. So case study, I'm trying di Penajam Pasir Utara East Kalimantan because location of Indonesia new capital city and a region with low seismicity. Focus azimuth analysis of low wave, mapping dominant propagation, direction, and source distribution. Seismic data are acquired from 30 seismometer station by operating from August 2022 to February 2023 with sampling rate 100 Hz. The network distribution across Penajam Pasir Utara Regency and Kutai Kartanegara Regency with interstation distance approximately ranging from 2 km to 85 km. The higher station density can acquire superior azimuth resolution and enhance about sensitivity with high frequency. Meanwhile, less than can sensitivity with low frequency. To processing data is follow about ambient noise interferometry to extra empirical green function. Continuous data, and try to divide it into daily segmentation, apparently only 600 seconds overlay with 450 seconds. To pre-processing, I'm doing bandpass filtering and remove mean and trend. And use temporal normalization using 1-bit normalization to remove higher amplitude from transverse wave such as earthquake. So I'm trying to analyze this low wave with take horizontal northeast component and try to rotate it to radial and transfer component. And try to the low wave extraction because when I'm trying to rotate it horizontal component with grid cycle path, transfer component perpendicular with grid cycle path. Cross correlation, I am try with tangential component and try the stacking over 6 months to enhance about the SNR and to acquire stable stacking for kilogram. And after I am resource taking, I'm taking about the period acausal and acausal to try to compare and determine about the noise distribution and noise source. In figure 3 display about 6 months of stack log cross correlation function between station IKN 0x and IKN 23 in the frequency range 0.1 to 0.6 Hz. Figure 4 display about 6 months of stack love wave cross-correlation function in the frequency range 0.1 to 0.6 Hz, computed with station IKN0X as the reference station. In the study, the cross-correlation were computed use the reference station IKN0X, and for the equation from question in cross-correlation is A cross B and B cross A. I'm take about A cross B. To use A is IKN0X and B is on the station to ensuring constantly interpretation of asymmetric component. For figure 4 is divided into two parts. Part 1 is causal part is positive leg, and negative part is a casual part. For a casual part have higher amplitude and coherent signal compared causal part, and several station part of a casual part nearly twice amplitude of a casual part. The superior evidence is clear arrival time at negative line 15 to 35 seconds indicate low wave propagations. Consistent velocity of 1 km per second is observed across multiple station pair. In figure 5, display about azimuth dependent of the normalized amplitude of cross-correlation function for a station pair within 0.1 to 0.6 Hz frequency range. In dominant source direction, I will try to divide it into three sectors. Sector 1 is eastern to southeastern sector, 90 degree to 135 degree. Highest amplitude, normalized one, and primary ambient noise contribution. 2. Northeast to eastern sector, 45 degree to 90 degree, significant elevated amplitude and secondary source regions. For sector 1 and sector 2, in the place about is study area. The pattern of figure 5 is the display about dominant distribution of noise and noise source. This figure 5 can highly pattern about the geographical location because for its geographical location about Makassar Strait. I'm trying to analyze this frequency 0.1 to 0.6 for ambient noise energy from cyclomicroseism in Makassar Strait. Makassar Strait have a deep flat 650 meter, and the Calabi Sea have deep flat about 680 meter. Sector 3 is western to southwestern. Low amplitude 0.4 to 0.6, weaker noise contribution. So, Karimata Straits and Java Sea have weak noise contribution for ambient noise tomography in Penajam Pasir Utara. Primary ambient noise contribution is Makassar Strait because Makassar Strait have speed wind approximately in month July to September is 4.5 km per second, with high wave is up 1 meter. In month December to January, we have about wave height is 0.7 to 0.6 meter. So, cross-correlation analysis, spatial heterogeneity of ambient noise source identified of through azimuth analysis. A causal component dominates with higher amplitude than the causal components. Station IKN0X used as reference for systematic cross-correlation analysis. Two source distributions, a main contribution source eastern to southeastern sector, we can contribution with the to southwestern sector. Oceanic source identification, Makassar Strait confirmed as primary ambient noise source, frequency range 0.1 to 0.6, and Java Sea, Karimata Strait, and Kalabesi relative weak contribution. Okay, thank you for your attention.
Okay, thank you for the presentation. Is there any question from participant? Okay, maybe we will break after azan. Okay, we will continue the Q&A session. Is there any question from participant? Okay, please.
Thank you. My name is Mudo Prakosa. I'm from Geophysical Engineering. As we already know that not all empirical green function we obtain from cross correlation depicting clear peak, right? The question I want to ask is, do you use all empirical green function before the azimuthal analysis, or do you do some selection before you do azimuthal analysis? Thank you.
Okay, thank you for your question. I will answer about your question. When I try about the cross correlation using 13 seismometer, I acquire approximately 78 empirical green function. I try the analysis azimuth use all empirical green function, but I determine empirical green function I can use is empirical green function on the signal of noise ratio approximately more than 5. So less than 5, I try to delete from process azimuth analysis.
Okay, the second question, is there any question for Mr. Iqbal? Okay, one more question, please.
Okay, thank you so much for the opportunity. My name is Farah Bushifa. I'm from Geophysical Engineering program study at ITB. Okay, for Mr. Iqbal, I have a question. From your presentation, I noticed that your results are still preliminary, right? And focus for cross correlation and stacking. Could you share whether this result can already be applied, for instance, to the development of IKN? And if not, what would be your next plan to advance the plan? Thank you.
Okay, thank you for your question. I will answer. My research still acquired about directional wave and noise source. In many researchers about ambient noise tomography is very important because ambient noise tomography come from random noise, done from earthquake distribution. In my research, still doing with Mr. Sriwidantoro, Julfa Krisa, and Nick Rollinson to determine about surface velocity in Penajam Pasir Utara, because from surface velocity can to determine about building etching and the prone about earthquake and other. So in my research still only distribution noise. To furthermore analysis, I can doing about surface velocity in Penajam Pasir Utara.
Okay, thank you, Mr. Iqbal, for a very interesting presentation. Okay, thank you. And we will move to the third presenter. The third presenter will be presented by Mr. Satria Aulia Rahman from University of Gajah Mada, with presentation title is Seismic Vulnerability Assessment Using Microthermal Data for Disaster Mitigation Based Development Planning in Wates Subdistrict Kulon Progo, Yogyakarta Special Region. So please, Mr. Satria.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, the distinguished professor, lecturers, researchers, student and moderator. My name is Satria Aulia Rahman from the Department Geological Engineering, Universitas Gadjah Mada. Today I will present my presentation with Mr. Agung Setianto and Mr. Wahyu Wilopo, entitled Seismic Vulnerability Assessment Using Microtremor Data for Disaster Mitigation in Basic Development Planning in Wates Subdistrict, Kulon Progo, Yogyakarta Special Region. Indo-Australian, Eurasian, and Pacific. This make earthquakes to be a part of our everyday reality. Yogyakarta is a clear example. In 2006, earthquake is still in our memory, showing how vulnerable this region is. Our study area, Wates in Kulon Progo, is now planned as a new urban hub and crossed by the Jogja Solo Toll Road to Bandara YIA. Development is in Kulon Progo. Development is accelerating, but seismic risk remains. That is why our research began here, to understand how the ground will respond and to support urban planning for the future. Next, the problem statement. On one side, it is planned as a new urban center in Kulon Progo Regency, supported by a toll road and regional development program. Yet beneath surface lies another story. Fragile alluvial deposit in the southern and central of Kulon Progo could cause severe damage to infrastructure during an earthquake if not properly addressed. However, until now, Wates has not had detailed seismic microzonation. This brings us to our core question: is which area are most vulnerable? How do local geology and sediment shape seismic response? And how can this knowledge guide safer disaster mitigation urban planning? And the research gap in this research is lack of detailed seismic vulnerability mapping for the water subdistrict and no clear basis yet integrated seismic risk information into spatial planning and infrastructure design. And the research objective is the first acquisition microtremor data across Wates, and next analysis dominant frequency and amplification using FSR method, and third calculate seismic vulnerability index, and next produce spatial distribution maps with the spatial method, and the last is recommended strategies for disaster resilient spatial planning. Next is my research location. Our study was conducted in Wates Subdistrict, Kulon Progo Regency, Yogyakarta Special Region. And based geology regional maps, this area shows a clear geology contrast. In the northern part and the some part in east is dominated by the Santolo Formation consisting of the limestone, marl, and tufaceous sandstone. This compact rock provides a relatively stable ground to condition. Meanwhile, the central and the southern part, southwest, are composed of alluvial deposits such as clay, silt, and loose sand. These unconsolidated sediment tend to amplify seismic shaking, making them more vulnerable. And my methodology is first we carried out microthermal measurement using a portable 3-component seismograph with each station recorded for at least 30 minutes to ensure stable data. And next, the data were processed in Geoscience software. We apply 25-second time window, used a bandpass filter from 0.5 to 20 Hz, and performed a fast Fourier transform to generate the spectral data. And then we calculate the horizontal to vertical spectral ratio result. The formula can be seen on the screen. From the half-Fisher curve, we extracted two important parameter data, that is the dominant frequency and the amplification factor. And after we get that data, we derive the seismic vulnerability index, which combine amplification and dominant frequency with that formula. And finally, we applied Kriging interpolation to create special maps of amplification, dominant frequency, and seismic vulnerability index, which allowed us to identify pattern of seismic vulnerability across the study area. This is a result my research. First result is the data amplification. Our analysis show that amplification value in waters range from 2.3 until 4.2 on the map, and we can see three main zones. In north, low value around 2.3 until 2.8, controlled by compact limestone and marl of the Central Formation. That is relative stable formation. And in center, moderate values 2.8 until 3.5, where alluvium mixed with central margin it means the moderate risks. In the south, high value up to 4.18, dominated by thick alluvium and loose water saturated and highly amplifying. Alluvial zone increase amplification and are more vulnerable, while the Central Formation is more stable. And next, result of dominant frequency. The result is dominant frequency range from 1.07 to 2.34 Hz, as on the map. In low frequency occurs in the southern and the central area with thick alluvial deposit, indicating deep sediment that are vulnerable to resonance with the low-rise building. Moderate in appears in transitional zone where alluvium overlap with the Central Formation, and high frequency dominant is found in the north where the compact limestone and marl and of the Central Formation produce more stable condition. In high frequency in so with color in blue color. In short, thicker sediment lead to lower frequency dominant and higher vulnerability, while bedrock produce higher dominant frequency and greater stability. And next, the result of seismic vulnerability index in water sub-district range from 0.93 to 25.08. From the map on the screen, we can see low seismic vulnerability index appears in the north, dominated by the compact rocks of the Santol Formation, and moderate in middle, and high in southwest part, where thick alluvial deposit make the area highly vulnerable to ground shaking and structural damage. The interpolation is clear. The higher the seismic vulnerability index, the greater the seismic risk. Importantly, many of these high zone overlap with the planned urban development areas in the plan NRTRW Kulon Progo, meaning this disaster mitigation must be a priority in future planning. Discussion and recommendation or findings show strong geological control over seismic vulnerability in waters. Alluvium show by high amplification, low frequency dominant, and high seismic vulnerability index. And Santol Formation is low amplification, high frequency dominant, and low seismic vulnerability index. And based on this, we recommend directing a critical infrastructure such as school, hospital, and government over to the northern and more stable zone, and enforcing strict earthquake-resistant building codes in high-risk zone, utilizing vulnerable areas for green space, open areas, or non-permanent use, ensuring that the Jogja-Solo toll route is reinforced where it crosses alluvial deposit, and integrating seismic mechanization maps into spatial planning policies to align development with disaster mitigation. In short, development in waters must always be guided by the seismic characteristic in risks at each location to ensure safety and sustainability. And the conclusion in this research is amplification and seismic vulnerability index are highest in the southern west alluvial zones, while frequency dominant higher and conditions are more stable in the north formation Santolo. In other words, local geology strongly control vulnerability, alluvial deposit amplify shaking, and while the compact rocks reduce it. Therefore, future development in waters must be careful, guide critical infrastructure should be placed in stable zone, while high-risk area require earthquake-resistant design or be used as open space. This way, waters can continue to grow, but in safer and more sustainability manner.
Okay, thank you, Mr. Satria, for the presentation. Is there any question from participant? Okay, please.
Okay, thank you so much for the opportunity. My name is Vera. I also happen to use the same method like Mr. Rahman, HPSR. So I found your presentation is very interesting. Since the study area is quite densely populated, like you said, which could affect the H-per-V curve and possibly lower the fundamental frequency, I would like to ask more about the process. How did you treat or adjust the parameters during your analysis to make sure the data quality is reliable? Thank you.
We take data in 30 minutes because we can remove the noise. And then And then the data we use the windowing to 25 seconds, and that method for the from the journal based the before research, the method which I use in the software Geopsy is that say they can the reduce the they make sure the data is can be used. And can you say ask again the question?
Okay, I think the time is over. Okay, you can discuss it after the presentation. Okay, thank you for Mr. Satria. Give applause to Mr. Satria. And then we move to the fourth presenter. The fourth presenter will be presented by Yulima Nurina Sutrisno, with the presentation title is Slope Stability Analysis of the Inlet Portal of the Krekeh Dam Diversion Tunnel using Limit Equilibrium Method. So please, Miss Yulima, the time is yours.
Okay, good afternoon, everyone. I'm Ulima Nurina Sutrisno. I'm here on behalf of my team to present about our study with a title of Slope Stability Analysis of the Inlet Portal of the Krekeh Dam Diversion Tunnel using Limit Equilibrium Method. Okay, so the Krekeh Dam is located at Sumbawa, West Nusa Tenggara. Designed for flood control and irrigation supply, supported by a diversion tunnel to redirect river flow during the construction. So the main challenge in this constructing the diversion tunnel is about the slope stability at the portal. Why at the portal? Because it's where failure may cause structural damage and safety risk. So therefore, this study was conducted. The stability assessment is carried out using the limit equilibrium method, or LEM, with Morgenstern, Price, and Spencer approach under static and pseudostatic condition. And then the analysis is supported by core drilling investigation, and then laboratory testing, rock mass classification, which is GSI, and numerical simulation using rock science slide software. And then the methods, the first one is geological strength index. So the GSI is assessed by two main parameters, which are discontinuity condition and rock mass structure. The discontinuity condition is represent the characteristic of discontinuity, such as aperture and then persistent, infilling, roughness, and weathering. And then Hook et al. At 2013 proposed an numerical equation to estimate GSI from discontinuity condition and rock mass structure, which is widely applied in geotechnical design of slopes, tunnel, and foundation. The equation is like as the screen. GSI equal 1/2 times Gcon 89 plus 1/2 of RQD. And then the second method is analysis of slope stability, evaluates the factor of safety using LEM under static and pseudostatic condition. And then based on SNE 8460/2017, the permanent rock slope, the factor of safety minimum 1.5, and then for temporary rock slope is 1.3, and for under seismic loading is 1.1. The seismic effects are considered through a pseudostatic approach, applying a horizontal seismic coefficient derived from peak ground acceleration, site class, and amplification factor. And then modeling was performed using rock science slide with non-circular slip surface, applying more column failure criteria for soil material, and then generalized sub-ground failure criteria for rock materials. And then FS values were calculated using Morgenstern price and Spencer method, which ensure full force and moment equilibrium in slope stability analysis. And then the result and discussion. The first one is about geological strength index. From subsurface assessment by core drilling and GSI, we got that the lithology at the slope, inlet slope, consists of tuff brachia and tuff, with rock bedding dips 16 until 70 to the southeast, parallel to the tunnel inlet, so it may affect the slope stability during the excavation. And then based on the weathering condition at inlet portal, the rock mass of the slope varies from highly until slightly weathered. And then from GSI assessment indicate that at the slope there's a sequence of poor tuff brachia at the surface with the GSI value of 23.93, and then fair tuff with GSI value of 43.2, and then good tuff with GSI value 73.75 at a greater depth. And then the second one is about seismic load. So the PGA value that we use for analysis is 0.359. This value is taken from LINI website by Ministry of Public Works. And then based on laboratory shear strength data, the soil is classified into soft soil following to the SNE 823/2016 with a site class factor of 0.9, and the adjusted ground surface acceleration is 0.3231 g. And then based on the equation 2, the corresponding seismic coefficient used in pseudostatic analysis is 0.16155. Then in the study, those soil parameters were not included into the assessment because the soil layer is less than 1 meter thick. So just the rock parameters that we use as a parameter input, which are unit weight and UCS, GSI, ME value, and disturbance factor. ME value is determined based on the lithology and uniaxial compressive strength, and then the disturbance factor is assumed to be 0 because based on the GSI assessment, we knew that the excavation that's suitable for the slope is ripping, so the disturbance factor is 0. And then the assessment was based on the preliminary inlet design by BBWS Nusa Tenggara 1 Mataram.
2 more minutes.
So this is the result of numerical analysis using rock science slide software. It indicates that this preliminary design is not stable under static and seismic load using Morgenstern price and Spencer method. So we need to do a geometry modification of the slope to improve the stability, such as benching and slope cutting, where benches increase the resisting force and slope cutting reduce the driving force. The optimized inlet slope design maintains an overall slope ratio of 1:1/2 with a 2-meter bench width and 2-meter safety berm. And from this assessment of the optimized design, we know that the safety factor under static load and seismic load with both methods indicate that the slope are now stable. So the conclusion is the inlet slope consists of two breccia with a poor quality and two with fair until good quality. And then the seismic coefficient that we use at this study is 0.16155, and then the result of the assessment of preliminary design show that the inlet slope is unstable under both static and seismic condition. And then after we do redesign of the preliminary design with bench and berm modification, inlet slope becomes stable. And then the redesign effectively improves the slope stability and provides a guidance for risk mitigation and engineering design in tunneling project at complex geological settings. I think that's all from me. Thanks for your attention. Now I'll turn back the session to the moderator.
Okay, thank you for Ms. Ulima for the presentation. Okay, is there any question from participant? Okay, please.
Good afternoon, Ms. Ulima. My name is Imran. I'm from Ministry of Public Works. Thank you for your nice presentation. I have a question related to slope stability analysis that you discussed. Considering that the factor of safety under seismic load is close to the minimum requirement, 1.1, how sensitive are your results to parameter changes? Thank you.
Okay, thank you for the question. I'll answer it. So the factor of safety is most sensitive in variation of seismic coefficient, horizontal seismic coefficient, and then groundwater condition and disturbance factor. So the horizontal seismic coefficient directly increase the driving force, so it will make the slope more critical under the seismic load. And then groundwater condition increase the pore pressure along the discontinuities, so it will reduce the normal effective stress and shear resistance, so it will decrease the factor of safety. So in many cases, to improve the slope stability, the first step that we do is lowering the groundwater table. And then the third is about disturbance factor. This value is reflects the degree of damage for this excavation. The higher the values will reduce the rock mass strength parameter in Hooke-Brown criteria, so it will lower the friction and cohesion, and it will affect the slope stability. Thank you.
Okay, thank you for Ms. Ulima for interesting presentation. Okay, thank you. Okay, we will move to the last presenter. It will be presented by Mr. Wahyu Trianggoro with presentation title is Engineering Geological Characteristic of Welikis Dam, East Nusa Tenggara, Indonesia. For Mr. Wahyu, please, the time is yours.
Thank you for Mrs. Moderator. Assalamualaikum warahmatullahi wabarakatuh. My name is Wahyu Trianggoro. In this presentation, I will present my paper, my study, Engineering Geological Characteristics of Walikis Dam, East Nusa Tenggara, with my co-author Hendy Setiawan and Mr. Akmaluddin. A comprehensive understanding of engineering geological properties is fundamental to the planning of a dam and tunnel construction, leading optimized outcome in terms of safety, technical execution, and financial viability. The Walikis Dam project site, located along the Mota Haliboyan River in Belo Regency, East Nusa Tenggara Province, Indonesia. As the part of the dam construction, diversion tunnel is required to reroute river flow during the construction phase. The plan of the diversion tunnel is designed with a horseshoe-shaped profile measuring 5 meters in diameter and 500 meters in length. In geological regional settings, in physiography, the research area located in Timor Island, East Nusa Tenggara, especially on the northern range area. And the research area lies on the geological regional geological map sheet Kupang Atambua Timor, which is composed by Noelle Formation, assigned as early Pliocene Formation, comprised by marl, tufaceous marl, biocalcarenite, sandy limestone, siltstone, and sandstone. Methodology in this research using surface geological mapping and across the area surrounding the tunnel alignment, subsurface investigation through the 6 boreholes, BT1, BT1A, BT2, BT2A, BD5, and BS1. Laboratory tests, including the uniaxial compressive strength, UCS, rock index properties, and photographic analysis and rock mass classification using RMR classification based on 5 parameters: weathering degree, UCS, RQD, discontinuity, spacing and condition, and groundwater condition. The result of the geomorphology in the research area defined by the basis of the morphography and morphogenesis. The site area divided by 2 geomorphological units. The karst hills unit, which the orange area on the map, and the alluvial plains unit, the gray area on the map. The surface lithology, geological mapping combined with the thin section analysis indicate the lithology of the study area can be subdivided to 3 distinct units: mud rock, the green one, limestone, the blue one, and the boulder sand deposit, the gray one. On the mud rock lithological unit, mud rock outcrop appear in dark gray with the fragments ranging to size of gravel and to the cobbles. The mud black to grayish, classic texture, clay size, carbonate bearing, and moderate to high weathering with some, there are intercalation of the sandstone in gray color, clastic texture, carbonate bearing, and poorly sorted. And the bedding orientation between 300 to 350 degree east with the deep angles 27 to 31. And the second one is the limestone unit characterized by white to gray with the fragment yellowish brown outcrop, comprise the radstone, wakestone, and crystalline limestone. Weathering grade varied to slightly weathered to highly weathered. The bedding orientation are measured between 6 to 10 degree east with the deep angles 8 to 10 degrees. The wakestone exhibit the white to yellowish brown colorization and with classic texture, grain size silk to the clay and generally good sorting. With in photograph micrograph of the wakestone consists range grain size to 0.04 millimeter to 0.6 millimeter, with massive structure, grain supporter fabric surrounded by grains, poor sorting, presence of interpellage and fenestral porosity, composite by 78% allochems, 18% micrete, and 4% mineral oxide. Crystalline limestone characterized by light gray colorization with non-plastic carbonate crystalline texture with low degree weathering. Outcrop distribute typically distribute on the top hilltop, and where dissolution process produce cavities. With the photographic micrograph crystalline limestone composed by dominated by calcite by 100%. Boulder and sediment. Boulders and sediment distribute across the plains surrounding the river, and predominantly along main course of Mata Haliboyan River. This deposit from breakdown from the older rock formation transported and deposited by fluvial process. The sedimentary accumulation range from sand to boulder, included identifiable components such as clastic limestone, crystalline limestone, and gravelly sand.
Two more minutes.
Okay. The surface the subsurface categorization conduct along diversion tunnel conduct data from 6 boreholes. The results show the groundwater level table position at the deep 4 to 15 meters below the ground and located above the tunnel planet elevation. The rock mass quality along the diversion tunnel dominated by wakestone falls into the poor category with RMR value ranging from 29 to 37. In general, the rock mass is slightly weathered with UCS value 1 to 5 MPa megapascal, indicating weak mechanical properties. And the conclusion, geomorphological conditions surrounding the area of the Welikis Dam are consist of the karst hills and the alluvial plains. The lithology are presented by three main units: mudstone, limestone, and sand boulder deposit. The groundwater table ranging from 4 to 15 meter below the ground surface and situated above the tunnel. And the assessment rock mass using rock mass rating system indicate the diversion tunnel across section largely dominated by wake-stone, categorized by poor rock mass quality with RMS value between 29 and 37. Thus, advised conditions are expected to be present considerable geotechnical challenges for the construction for the diversion tunnel. Thank you for your attention.
Okay, thank you for Mr. Wahyu for interesting presentation. Is there any question from participant? Okay, please.
Good afternoon. My name is Niken. I am from Directorate General of Highways, Ministry of Public Works. Thank you for your presentation, Mr. Wahyu. I wanted to ask to you, we know that there are many classification systems available for geological setting. Why did you choose to use rock mass rating or RMR system? Thank you. Okay.
Thank you, Mrs. Niken. Why I'm use RMR system with classification rock mass classification, which is RMR commonly used in the geological engineering, which is we can communicate with another location or research with RMR classification and data collecting, which weathering degree, UCS, RQD, spacing, discontinuity spacing and condition, and groundwater condition. Thank you.
Okay, is there enough? Okay, is there any more question for Mr. Wahyu? Okay, thank you for the presentation, Mr. Wahyu. And to all the presenter, I said thank you for a very insightful and interesting presentation. We appreciate your time and engagement, and we move to the second technical geophysical session, and will be moderated by Dr. Farid Nizar from Geophysical Engineering ITB. And now maybe coffee break first. Okay. Okay. We will give the certificates to all the presenter. So please, for the 5 presenter to receive our certificate. Okay, maybe from the first presenter, Mr. Marianto. Okay, thank you, Mr. Marianto. And the second is Mr. Iqbal Ramadan. Okay, the third presenter is Mr. Satria. Mr. Satria from UGM, I think. Okay, next. The fourth presenter is Miss Ulima Nurina. Okay, and the last presenter is Mr. Wahyu. Okay, and the last for me.
Thank you very much for Ibu Dona Sita Ambarsari to run these sessions. And ladies and gentlemen, we have a coffee break in the back. You can have the coffee break sessions for 5 minutes, yeah, because after this we still have two last speakers of this geophysical session. Please enjoy and directly go back to your seats. Thank you. To the poster presenter who haven't received the certificate of appreciation can contact to the committee. Pengumuman juga bagi yang merasa kehilangan kunci motor berwarna hitam boleh menghubungi ke panitia. Terima kasih. All right, ladies and gentlemen, we are now arrived at the very last event, still the third technical session that will be led by Bapak Hafiz Nizar Ahmadi. To Bapak Hafiz, you may come to the stage.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Today, we will have the last oral presentation, the last session, and there will be two presenters with the topic of first oil and gas exploration, and then the last topic will be earthquake seismology. So let me introduce myself first. My name is Farid Nizar Ahmadi. I am a lecturer from Geophysical Engineering, and currently my specialty in gravity and magnetic. And also, I am the moderator in this session. And I would like to, before the presentation, I would like to remind the presenter you will have only 15 minutes for your presentation to present your idea, including question and answer session. And the portion will be 12 minutes for your presentation, and then next will be a question and answer, the last 3 minutes. I will give you a reminder if the time is very nearly to the end. So please keep in mind to stick to the timeline to manage your presentation. So moving to the first presenter. I would like to invite Mr. Simanjuntak to the podium. Is there any Mr. Simanjuntak? Okay, he will present about the supervised machine learning for pore and mineral identification of CT scan image of digital rock image analysis in deep water reservoir. This is very interesting presentation if you are really interested in the oil and gas industry. So, time is yours, Mr. Simanjuntak. You will have only 15 minutes for your presentation. The last 3 minutes, I will give you a reminder.
Okay. Good afternoon, everyone. My name is Abisa Kesaruli. I'm Simanjuntak, or Abisa. Thank you for ICGRE for giving me a moment to show my research with Mr. Fatkan and Ms. Madania about unsupervised machine learning for pore and mineral identification of CT scan images, digital rock image analysis in deep water reservoir. So the project today is we go to introduction. There was background, ERP, and ML. So what's the problem based on this research is in the oil and gas production, the reservoir quality is the important point to know about how will the oil and gas will be get extracted. So to know about reservoir quality, it depends on porosity and mineral composition. The porosity will we know about the porosity is for use about how much the fluid in there, and the minerals is how good the quality of the reservoir it be. And to know about the reservoir quality, we have the traditional methods, but the challenges is the traditional method is so slow, costly, destructive, and we need something that fast and non-destructive and automatic workflow. So I introduce you about the digital rock physics. So basically digital rock physics is about to know about what is the rock in digital. So we have a file or data from a rock that from the CT scan imaging that we apply the physics simulation to know about the physics aspect from the rock itself. We can know the porosity, the density, and etc. So the advantages is efficient and is microscopic precision. But the challenge is the data itself from the digital rock physics is so massive. It's so many images, sequential images that we must to know about the complexity of the pixels, and if we apply the traditional methods to the digital rock physics data, it will have a long time to learn about it, and it's inefficient. So the workflow basically is from the CT scan, and then we get the pre-processing, and then we have the segmentation for the data pixels, and we apply the physics simulation. So the solution about the DRP itself is we apply the machine learning. The machine learning is basically is a computer unsupervised or supervised will know about how the data work. It's automated, objective, and scalable. So we use grayscale intensity pixel as the features about the data, and we can discover the hidden patterns without labeling. So the methodology is about the data CT scan, and then we get the normalization, and then the clustering. For the geology aspect from the sandstone sample itself, it's from the Kutai Basin. So Kutai Basin is one of the largest hydrocarbon basin in Indonesia. Basically, Kutai Basin have two sides. Is Upper Kutai that dominantly is uplifting effect and erosion, and then a Lower Kutai that create in the Miocene era that dominantly is from sandstone, and it's basically the main reservoir. So for the data we use for different data, but it's the same place. So the first data is mainly the CT scan core sandstone sample. So the sandstone will be scanning with CT scan, and we have the sequentially image about the data itself. And then we have a well log data from the well that the sample is be taken. And then we have a thin section petrography of the sandstone to know about how the structure and texture from the sandstone. And then we have the XRD result of the sandstone sample. So the first data is a data CT scan core sandstone. It's the sample from the CSR well, diameter from approximately 50 millimeters. And from the CT scan imagings, we get the sequential image about 1,404 slices. And we check just a part of the image itself is around about 700 slices. Because the 700 slices, we make sure that the image is right the inside of the sandstone itself. And each slice we cut to get 900 by 900 pixels, and roundly approximately it's about 13.5 millimeter in physical. So we make sure it's the data itself is high resolution, and the CT scan image is not disruptive, meaning it's not affect physically with the sandstone, and it's itself have a microscopic scale. And then we have a data type well log. So data well log is represent a physical properties near the core plug. So it can validate porosity results from the CT image and show rock heterogeneity and vertical continuity. So we use porosity total value to know about the roughly of the porosity of the rock itself. And we get the value at about 1360 feet. And then we have data thin section spectrography. It's taken from the same core as the CT scan, and it has the direct spatial correlation. It provides it contains the percentage of the component of the minerals, but it's sometimes not accurate because it measured is by the person, so sometimes it's subjective. And then we have data X-ray powder diffraction, or XRD. So basically, XRD, it gets from the X-ray diffraction from the crystalline powder of the sandstone itself. So it can identify crystalline minerals with XRD, and the main result is dominantly is quartz 76%, and the others miners component other mineral. So this data can validate the city's clustering and complement petrography and Wheelock's objectivity. So next, after we get the CT scan data, we check a normalization to the data itself. So basically, so this is some of from the 700 slices before, we show some of the three part of the slice. So we can see that slices in this slide looks dark, and almost we can see the minerals from the core. So we take a normalization with VG imaging to change from a DCOM data to the PNG data, and change convert the 60-bit histograms color intensity to 80-bit, because in 60-bit it's dominantly still have a zone that contains artifact and noises. So we cut at the right part where the intensity is the sandstone itself. So this is after the normalization. This is just some 6 CT scan slices after normalization within one data sequence. So from the 700 slices before, we can see that that's the 3D version of the sandstone. So to process the normalization data, we use two machine learning. It is fuzzy K-means or FCM, and Gaussian master models. Both is unsupervised clustering, and subclustering, so pixels can belong to multiple cluster. And this is good for mineral transition areas, but is sometimes sensitive to initialization. As we can see this in this slide, the algorithm is make sum of the part objective function, and the algorithm we can find the objective function from the C number of cluster. So we check the numbers is 5 because we cluster to be a 5 cluster, and then n as a number of data points of the how much pixel it's in the image itself. So 9,000 by 9,000 pixels, and then the xg for the data pixel intensity, and then a v for the cluster centers, and then u for membership degree of the xg in cluster, and then m as the fuzziness parameter. So the fuzziness itself is about how the algorithm create the membership of the data itself. And then we have a Gaussian mixture model or GMM. It's a probability-based soft clustering that can handle overlapping data and can underestimate pores sensitive to local solution. So as we can see from this slide, there are some pixels that overlap in the 2 or 3 Gaussian distribute. So in the algorithm, they can work to labelize unsupervised which of the cluster the pixels gonna be. So we can see of the algorithm itself, there's a probability, as a number of cluster, and that's probability weighted, and the Gaussian distribution.
3 more minutes.
Next. And then we have a result and discussion. So the clustering itself, we get to know about the percentage or in the range of pixels from the FCM and GMM. Next. And then this is a vertical distribution of the clustering result from the 700 CT scan slice from FCM and GMM. So we can see in this slide that in the FCM, from 1 to 700 slices, they basically it's can we say it's a good clustering, better than GMM, but both in the big picture it's good clustering. This is just slice 1 from the result of the FCM and how much the percentage of each cluster. We can see that pori and the pore 0 is 3%, and the dominantly is the mineral 1 as the 32%. This is 6 slices from the 700 slices. Next. And then this is like a video or a GIF from the slice 1 to 700 slices. So we can see the algorithm is basically works just fine, that can show which of the pores and the minerals, and there's no sometimes and then this is GMM visualization results from the slice 1 and the histogram from the percentage area. So dominantly it's still in the mineral 1, but there's underestimate in the mineral 3, there's 1%, there's only 1%. This is 6 slices from the 700 slice. And then this is a video or GIF from the slice 1 to 700, that we can see that basically in the pore 0 and pore 1 is the algorithm works perfectly fine, but sometimes there are some jumping from the mineral 1 to mineral 2 clustering. But the mineral 3 is still fine. So how to know about how good the percentage we get from the clustering? So we use the other data to validate the results of the clustering. So for the well log, we check the porosity total to know about the total porosity. So the total porosity from the total percentage of the sandstone is, we can say, it's 25%. And then for the SRD, we use it for to know about how much of each minerals it's gonna be. So in the mineral 1, we can see it's dominantly from quartz. We check just like that. And mineral 2, we choose which mineral that can match about the geology aspect. It's alite and albite. And mineral 3 is kaolinite siderid calcite, that because there are the minor minerals. So we group the percentage and we conclude that the percentage is like for the slide. So mineral 1 is 57%, mineral 2 is 9%, and mineral 3 is roughly 7%. So this is a total cluster versus the reference number before. So yeah, FCM and GMM basically doesn't really match with the reference data, but we can see that for some pattern, we can see that in the mineral 1 and from the reference and FCM GMM is still dominantly, and the mineral 3 is in a minor mineral, and the GMM mineral 1 is the most almost match from the mineral 1 in the reference data. And for the thin section photometry, we use this just for to know about is it really a match texture from the same sandstone? So yeah, and at the clustering result comparison from FCM and GMM, we can see that the texture is same. So we can conclude that the geology, the process from the sandstone itself is basically same and works fine. So what we can conclude from this research is there are two surface clustering methods that successfully segmented pores and minerals from the sandstone sediments image. FCM is closer porosity estimate to log data. It's stable across slices but tends to overestimate minor minerals. And GMM is smoother boundaries, adaptable to intensity variation, but underestimate pores and carbonate. Both methods consistent with well-logged SRD in seismography, and the integration and FCM GMM enhance digital rock physics workflow for deep water reservoir characterization. So and then acknowledgements. So I gratefully acknowledgement for the Dr. Farkan and Ms. Manadinya for their valuable guidance. Appreciation is also extended to my family and colleagues. And the outdoor and me myself also acknowledge the research funding support from BTM to IITB. And then this is my reference to the research. And that's all for my research. Thank you for your attention.
Okay, thank you for Mr. Simanjuntak. I would like to invite the audience to have short questions. Okay, please.
Check. Good evening, everyone. Thank you for the presentation. Let me reintroduce myself again. My name is Daniel, and I would like us to Mr. Simanjuntak, if I'm not wrong, if this technology will be implemented in full field scale, because the technology is really interesting. I was wondering what will be the input data so that the machine learning will give a good result that will represent the condition of the field, especially about the porosity. Thank you.
Okay.
Okay, thank you for the question. So the question is how gonna be so we what measurement is right for the project, so we can get the right number in the next research project. Yeah. Yes. So from what I do in this research, the correction is we get sometimes bad results, bad numbers, is because we use the unsupervised clustering. So sometimes the algorithm itself doesn't correct the which of the clustering that this is a mineral, this is a pores, because this is unsupervised. So there are no sorting. So for which of the data so we can use to be good results is basically XRD, thin section, and well-log is work just fine. Just is it not good as we much predict? Is because just the clustering we use for this research. So for the next research, I hope someone can use this, but with supervised clustering or other machine learning itself. Thank you.
Okay, thank you for Mr. Simanjuntak for your presentation. Really interesting presentation. Please give applause to Mr. Simanjuntak. Okay, moving to the last presentation today, we will have Mr. Nabil Visi Samawi from Bandung Institute of Technology. He will present us about the reform. refinement of earthquake location in Central Maluku using hypo-DD based on double difference method. Please, Mr. Nabil, time is yours.
Okay, good afternoon, everyone. For the distinguished committee and fellow participants. And I would like to say thank you and give my respect to you guys for to waiting until the end of the day. And my name is Nabil Fisi Samawi from Bandung Institute of Technology. Today I will present my research entitled Refinement of Earthquake Location in Central Maluku using the hypo-DD based double difference method. Next. Okay, next. Okay. So, we talk about the background and motivation. So, the Banda Arc is a very active tectonic region where the Indo-Australian or Asian and Pacific plates converge. Routine earthquake catalogs from BMKG are based on 1D velocity model. While this method is fast, it introduces large errors in earthquake location. As a result, hypocenter appear scattered and diffuse, which makes it difficult to identify active faults or lineation. This motivates the use of relocation methods, in particular hypo-DD, to generate a more reliable seismicity pattern. Okay, next. Next, okay, into the objective slide. Okay, so the objective of this research are threefold. First, to relocate earthquake in Central Maluku between 2015 and 2019 to improve their location accuracy. Second, to build a high-resolution seismicity catalog from the relocated events, which can serve as a reliable reference for future studies. And third, to identify hidden tectonic structures, especially the Banda Fault, which is the most important active faults in these regions. Next, please. Okay, next. Okay, hypocenter relocation means recalculating earthquake location to reduce uncertainties. This is crucial because precise earthquake location are fundamental for seismotectonic interpretation. For example, diffuse seismicity can often transform into clear lineation after relocation, making active faults more visible. Therefore, relocation is not just a technical adjustment, but a key step in understanding tectonics and hazard, seismic hazard. Next slide, please. Okay. So, we talk about the hypo-DD. Hypo-DD or double difference method is a relative relocation technique developed by Waldhauser and Ellsworth in 2000. The principle is, if two earthquakes are close and recorded at the same station, their travel paths are nearly identical. Thus, the difference in their arrival times mainly reflects their relative location. This concept is expressed in this equation here. The double difference residual is the observed travel time difference minus the calculated travel time difference. By minimizing the residual through iterative least square inversion, we obtain more accurate relative location of earthquake pairs, which produce a sharper seismicity pattern. Next slide, please. Okay. In Indonesia, earthquake location are usually determined using single event. methods with 1D velocity model as practiced by BMKG. While sufficient for rapid monitoring, this approach produced diffuse hypocenter and fault planes that are unclear. HypoDD is needed because it minimizes the impact of unmodeled velocity heterogeneity by using differential times between even pairs. As a result, HypoDD reduces residuals, improves clustering, and reveals hidden fault lineation that conventional methods cannot. Next slide, please. Okay. The study area in Central Maluku within the Banda Sea region, known for complex subduction and collision tectonics, we analyzed 1,276 shallow earthquakes with depths less than 60 kilometers recorded between 2015 and 2019. The dataset came from 21 BMKG seismic stations shown here on the map. The input data include arrival times of P and S webs, which were pre-processed and formatted for relocation using PH2DT and HypoDD. Next slide, please. Okay. So we talk about the methodology, and it's same we talk about the workflow. The workflow is begin with PH2DT, which pre-process the catalog to select earthquake pairs recorded at common station and compute differential travel times. Key parameters such as maximum separations, distance, and number of neighbors are applied to ensure quality. The output differential time data is then used as input for HypoDD. In the HypoDD stage, relocation is performed iteratively, minimizing residual and refining even coordinates. Finally, validation is done by checking RMS residual and comparing before and after patterns, followed by tectonic interpretation. Okay, next. Okay, here's for the before relocation. Before relocation, earthquake location were scattered and diffuse. The RMS residual was still high, about 0.786 seconds, which shows large travel time errors. In the cross-section, even appear as diffuse clouds, and the Banda fault could not be clearly identified. This illustrates the limitation of conventional single event location methods with one model, it's 1D models. Next. Okay, here's the after relocation. After relocation, 1,273 events were successfully relocated. The RMS residual decreased drastically from 0.786 seconds to only 0.020 seconds. This dramatic reduction validates the effectiveness of the HypoDD method. More importantly, the relocated hypocenter, now from a clear north-south lineation consistent with the Banda fault. This proves that the Banda fault is seismically active and can be well mapped with this method. Next. Next, okay. Maybe you blink your eye and here's the comparison. This slide highlights the improvement very clearly. On the left, before relocation, earthquakes are diffuse and scattered. On the right, after relocation, the same events form a tight cluster and that align with the Banda fault. This side-by-side comparison shows that the HypoDD not only reduces residual statistically, but also greatly improves the tectonic interpretability of earthquake catalogs. Next slide. Okay. This histogram, as you can see in the screen, shows the residual distribution before and after relocation. Before relocation, residual were widely spread around 0.8 seconds, reflecting poor data model fit. After relocation, residual become narrow and center close to zero, with RMS reduced to 0.020 seconds. This strong statistical evidence confirms that hypodidi significantly conclusion. 3 main points can be drawn. First, hypodidi significantly improved the accuracy of earthquake location in central Maluku. Second, RMS residual decreased from 0.786 seconds to 0.020 seconds, confirming the effectiveness of the methods. Third, the relocated seismicity, a clear north-south banda faultination, is providing stronger tectonic interpretation and potential input for seismic hazard study in the region. Okay, next slide. Okay, here are the main references for supporting this research. Okay, thank you for your attention. I hope this presentation has shown how hypodidi can refine earthquake locations and reveal active tectonics structure in Indonesia. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Okay, thank you for Mr. Nabil. And then the next will be, I would like to invite the audience. If you have any question, please raise your hand and grab the phone, the microphone. Is there any questions? Okay, please.
Okay, I'm Hana, and my question is, what are the limitations or challenge of using hypodidi for earthquake relocation in this region? Okay, thank you.
Okay, that is very good question, Ms. Hana. So, I want to answer your question. So the answer is, it requires dense seismicity and sufficient number of stations. If the data is sparse, the improvement will be limited. That's the answer.
Okay, is there any more questions from the audience? So from the discussions, you know that if the data very sparse, it will be, you need to recheck, and you need to recheck the method, is it good or not. No questions? Since there is no questions, maybe the times is also up. I would like to thank Mr. Nabil for very insightful discussion and presentation. Please give applause to Mr. Nabil. And next will be the okay, please, for the last two presenter, please come forward. We will present you with the certificates of the presenter. Okay, thank you. Please give applause to the presenters. And before closing, I would like to thanks to the committee and then for the chairman in the ICGIRI. Thank you very much to give me opportunity to be a moderator in this oral presentations. For the next agenda, I will like to give the MC. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much to Bapak Farid Nizar Ahmadi to run these sessions. And ladies and gentlemen, finally we are at the end of the ICGRE annual event. On behalf all of the organizing committee, I would once again give thanks to all the audience for all the time, effort, and also the all thinking that has been poured into the oral and the poster presentations. We have received a lot of incredible results in these 2 days, and we hope of our work will give a significant contribution to the development of geoscience and the energy resources aspect, especially in Indonesia. And we also want to apologize of any mistakes or inconvenience even during this year ICGRE, and we will back in the ICGRE next year. Please take care of your way back home and see you in the next year. Wassalamualaikum warahmatullahi wabarakatuh. Cek, untuk yang merasa kehilangan kunci motor dengan gantungan warna hitam ya mungkin bisa menghubungi ke panitia ya. Untuk yang merasa belum menerima piagam juga bisa menghubungi panitia untuk pengambilan selanjutnya.